In February 1977, the water above the submersible was still blue. Then it was indigo. Then it was a color that has no name because no light reached it from above, and the only illumination came from the small craft itself, moving downward through more than 2 kilometers of the Pacific Ocean, its hull carrying 3 people into a darkness that had existed, uninterrupted, since before the first fish swam. The descent took 2.5 hours. During those hours, the pressure outside the vessel climbed. It climbed past the point where an unprotected human body could survive. It climbed past the point where most materials compress and fail. The temperature of the surrounding water dropped to just above freezing and stayed there, and the darkness outside the porthole windows was total, not the darkness of a room with the curtains drawn, not the darkness of a clouded night, but the darkness of a place where daylight has never once arrived, where no surface, no particle, no molecule has ever been touched by a photon falling from the sun. The submersible descended through this absolute condition, the way a stone sinks through still water, slowly, steadily, with no drama to mark what was happening. What was happening was that 2 men were going to a place no person had ever been. The submersible was called Alvin. It was white, roughly the shape of a large egg, built to withstand pressures that would crush ordinary steel. It had been commissioned in 1964 by the Woods Hole Oceanographic Institution and had been diving ever since, accumulating a history of descents into places the surface world had never seen. Its pilots had learned, over years of ocean work, to read the bottom as it came up slowly in their exterior lights, the gradual brightening of sediment, the way the seafloor resolved out of the dark above the last few meters of approach, the pale gray of abyssal mud giving way to whatever lay beneath it. On this particular February morning in 1977, the seafloor below was not ordinary. The 2 geologists aboard were Jack Corliss and Robert Ballard. They had come to a region of the Pacific known as the Galapagos Rift, a place where 2 vast sections of oceanic crust were pulling apart from each other along a deep crack in the seafloor, a wound in the planet's outer surface, roughly 2.5 kilometers below the surface of the sea. The rift was a place of geological youth, where new rock was being formed continuously from material welling up from below, where the crust was thin and the heat of the Earth's interior was close. Geologists had suspected, on theoretical grounds, that water might be circulating through such rifts, that cold seawater might find its way down through cracks in the new rock, be heated by the warmth below, and return to the ocean floor transformed. They had come to look for signs of this. They had brought instruments to measure temperature anomalies in the water. They had brought cameras. They had not brought adequate preparation for what they found. As Alvin's light swept across the seafloor at 2.5 kilometers depth, the instruments registered a temperature anomaly in the water. The readings climbed. The pilots slowed their approach, and then the cameras resolved from the surrounding dark, something that no one in the history of science had ever seen from a submersible window, a cluster of living organisms, dense and various and entirely present, gathered around a column of shimmering heated water rising from a crack in the volcanic seafloor. There were animals there, many of them living in the dark at 2.5 kilometers depth in water of nearly freezing temperature, sustained by nothing the scientists could immediately account for. The nearest sunlight was kilometers above them. The nearest photosynthesis was the same distance away. By every existing framework for understanding where complex life could exist and how it sustained itself, there should have been nothing here but cold sediment and bare rock. The word that Corliss transmitted to the surface team, waiting on the research vessel above, has been recorded. He said, among other things, that the water was warm. He said there were organisms. He said it was hard to describe. The scientists on the surface ship, reading the transmitted data, understood that something significant had happened, though none of them yet had the framework to say exactly what. It would take time to build that framework. It would take the work of many researchers across many expeditions, using tools and methods that didn't yet exist in 1977. But the moment of discovery was complete, contained, final. The world in which life required sunlight had ended at that particular set of coordinates on the Pacific seafloor in that particular February, and the world in which it did not had begun. Before any of that could be understood, the place had to be reached, and to understand reaching it, it helps to understand the seafloor itself, the geography of a world that exists in conditions almost nothing on the surface resembles. The ocean covers more than 2/3 of the planet's surface. Its average depth is roughly 2.5 miles. Most of it, the enormous middle portion between the surface and the deepest trenches, is cold, dark, and largely empty of life. A volume of water so vast that all the continents combined could be set inside it, with space remaining. Below this water, invisible from any ship's deck and inaccessible to any diver, lies the seafloor, a terrain as varied and as extensively featured as any above the surface, but unlit, unphotographed across most of its extent, and until very recently entirely unknown. The seafloor has mountains, it has plains, it has canyons deeper than any on land, and trenches deeper still, dropping to depths where the pressure is more than 1,000 times that at sea level. It has volcanoes. It has fields of mineral nodules that have been accumulating for millions of years on the abyssal mud, growing at rates too slow to measure without instruments designed for the purpose. It has distributed across it in a vast, continuous system, unlike anything else on the planet, a feature so large and so geologically significant that its discovery changed the understanding of how the Earth itself works. Along the floors of every ocean basin in the world, a chain of underwater mountains runs continuously. This chain is called the mid-ocean ridge system. It is not one ridge, but many connected sections, running through the Atlantic from north to south, cutting across the Indian Ocean, threading through the Pacific, connecting through smaller sections that link the major basins together. Its total length is roughly 60,000 kilometers, longer than any mountain range on land, longer than all the terrestrial mountain ranges on the planet combined. Its peaks rise thousands of feet from the surrounding seafloor. Its valleys are deep enough to shelter the tallest buildings ever constructed, with room to spare. And across most of its 60,000 kilometers, no human eye has ever seen it directly. The mid-ocean ridge system is the longest continuous geological feature on Earth, and it is almost entirely invisible from the surface. It runs through water too deep and too cold for any human diver. It runs through darkness that no surface light can penetrate. Its peaks in most places still sit well below the reach of sunlight. To know it at all is to know it through instruments, through sonar signals that bounce off the rocky slopes and return to surface ships as numerical data, through the records of remotely operated cameras, through the slow accumulation of readings taken by submersibles on expeditions that are each individually brief in comparison to the geological scale of what they are studying. To understand why the ridge exists, it is necessary to think about what the Earth's crust is doing. The crust that forms the floor of the ocean is not fixed. It never has been. The enormous plates of rock that make up the surface of the Earth are in motion, driven by the slow churning of the hot mantle rock beneath them. Where two oceanic plates pull apart from each other, the crust thins, and hot material from the mantle wells upward to fill the gap. This upwelling rock cools as it meets the ocean water, forming new seafloor. More rock wells up, pushing the new crust sideways, and the plates continue to spread. The ridge marks the place where this spreading happens, where new ocean floor is being born continuously, where the crust is thin and warm and geologically young. Along the East Pacific Rise, the spreading happens relatively fast, several inches of new seafloor every year, which is fast in geological terms. The faster the spreading, the more heat is available near the surface of the new crust, and the more intense the hydrothermal activity that develops along it. In places of fast spreading, the vents that form are driven by extreme heat from magma chambers close to the surface. Their fluids reach temperatures above 350 degrees Celsius, well above the boiling point of water at the surface, kept liquid only by the immense pressure of the ocean above them. The chimneys they build, from minerals precipitated out of the scalding fluid, are dark and dense and sometimes meters across. Along slower spreading ridges, the Mid-Atlantic Ridge, for example, where the spreading rate is measured in fractions of an inch per year, the geological story is different. The crust is thicker in places, the heat from below less immediately available, but slower spreading comes with its own kind of hydrothermal activity, driven not only by the heat of magma, but by something more fundamental: the chemical reaction between seawater and the rocks themselves. The cold seawater that percolates down through cracks in newly formed oceanic crust does not simply pass through unchanged. The rock it moves through is made of minerals that are chemically reactive in the presence of water. As the seawater descends, sometimes several kilometers into the rock, following fracture networks that branch and connect in the darkness of the crust, it begins to interact with the mineral surfaces around it. The rock absorbs components of the seawater. The seawater absorbs components of the rock. Heat is produced. The water changes, chemically and physically, and then, enriched and transformed, it begins to rise back toward the sea floor, driven by its own heat, forced upward through whatever fractures and channels the rock provides. This is the basic mechanism of a hydrothermal vent system. Cold seawater descends through cracks. Heat and chemistry transform it. Transformed fluid ascends and exits back into the ocean. The cycle runs continuously, driven by the heat of the planet's interior and the persistent flow of cold seawater seeking the cracks in new rock. It has been running in one form or another for as long as oceanic crust has existed, which is to say, for most of the Earth's history. More than 700 hydrothermal vent fields have now been identified or inferred across the mid-ocean ridge system. 700 named locations scattered across 60,000 kilometers of underwater mountain chain, each representing a place where the cycle of descent and ascent is producing something visible: a plume of altered fluid, a field of mineral chimneys, a community of organisms gathered in the warmth. 700, and the ridge system remains largely unexplored, with long stretches of its length never visited by a camera or a sensor of any kind. The true number of vent fields may be considerably higher. Each vent field is different. Each reflects the specific geology of the section of ridge it sits on, the spreading rate, the rock type, the depth, the chemical character of the seawater circulating through that particular piece of crust. Some vent fields are small, a few chimneys clustered around a single fracture. Some are large, spreading across hectares of seafloor, with dozens of active structures venting fluid simultaneously. Some are geologically young, having formed within the last few decades. Some are ancient, having been active for tens of thousands of years. All of them were discovered the same way: slowly, carefully, by small vessels descending through enormous depths of cold, dark water. Alvin is the instrument through which most of what is known about hydrothermal vents was first learned. It has been modified and upgraded many times since its commissioning in 1964, its original components replaced and improved until it is in many ways a different craft from the one that first went to sea. But its purpose has remained consistent: to carry scientists to the deep sea floor and allow them to see, collect, and measure what is there. Over more than 5,000 dives, it has been the primary means by which the vent fields of the world's ocean basins have been located, examined, and understood. Alongside Alvin, and alongside similar human-occupied submersibles from other nations' research programs, the exploration of the deep sea floor has been extended by machines that carry no people. Remotely operated vehicles tethered to surface ships by long cables, controlled from above, equipped with cameras and manipulator arms and instrument packages, can spend hours or days on the seafloor while their human operators watch from the warmth of a ship control room. Autonomous underwater vehicles, untethered and pre-programmed, can travel hundreds of kilometers along the seafloor in a single dive, mapping terrain and detecting chemical signals that may indicate the presence of undiscovered vents. These tools together form the means by which the hidden world of the deep sea floor is being slowly, incrementally revealed. The revealing is incomplete. It will remain incomplete for a long time. The ocean floor covers more than 330 million square kilometers, and the fraction of it that has been directly observed at close range is a small portion of that total. Most of the mid-ocean ridge, most of the 60,000 kilometers of mountain chain, most of the 700 or more vent fields, most of the geological and biological complexity that must exist along its length remains in the same condition it has always been: dark, cold, pressurized, and unknown except in the broadest outlines that sonar can provide. Alvin descends to a given site. It illuminates a cone of seafloor, perhaps 20 meters across. It observes for a few hours. It ascends. The seafloor beyond the cone of light continues as it was. In December of the year 2000, a team led by the oceanographer Deborah Kelly of the University of Washington discovered a hydrothermal vent field unlike any previously known. The discovery came not at a mid-ocean ridge spreading center, but on a feature called the Atlantis Massif, a broad, flat-topped underwater mountain rising from the Atlantic seafloor roughly 15 kilometers to the west of the mid-Atlantic ridge. The Atlantis Massif is not a volcanic structure in the conventional sense. It is an uplifted block of old oceanic crust, pushed upward by tectonic forces and exposed at the seafloor, its surface composed not of the relatively young basaltic rock, typical of mid-ocean ridges, but of older, deeper material, rock from the mantle itself, brought close to the surface by the same forces that built the massif. The summit of the Atlantis Massif sits at roughly 700 to 900 meters below the ocean surface. This is shallow for a hydrothermal vent field. Most known vent systems sit much deeper. Alvin's 1977 discovery was at 2.5 kilometers, and many black smoker fields sit at similar depths or greater. The Atlantis Massif is shallower than almost any other major hydrothermal site, close enough to the surface that the pressure, while still far beyond what the human body could bear unaided, is less extreme than at the deepest vent fields. Across the surface of the Atlantis Massif, the December 2000 expedition found chimneys, not the dark metallic chimneys of the black smoker systems, not the dense sulfide-crusted structures that other teams had found along faster spreading ridges. These chimneys were white. They were pale and delicately structured, their surfaces textured in ways that resembled coral or frost. their forms rising from the rocky seafloor in clusters and in isolated spires. The tallest of them reached heights that dwarfed a person, structures of carbonate mineral built slowly over long periods of time, still actively venting fluid from their upper surfaces. The team named the field Lost City. The name carried a quality the place seemed to warrant. The pale chimneys rising from the flat-topped underwater mountain did look, in the lights of the remotely operated vehicle that first recorded them, like the ruins of something, structures that had been standing for a very long time in a place no one had known to look. Their whiteness against the dark seafloor was striking. Their scale was striking. The fluid venting from them was not the violent superheated jet of a black smoker, but something gentler, a slow, warm rise, barely visible as a shimmer against the cold water above. The discovery of Lost City added a new dimension to an already complicated picture. The understanding of hydrothermal vents that had developed in the decades since 1977 had been built primarily from the study of black smoker systems along faster spreading ridges, the East Pacific Rise, the Mid-Atlantic Ridge's spreading center, the Indian Ocean's active zones. These systems were well described, their chemistry known, their biology extensively studied. They fit a coherent model: magmatic heat driving the circulation of seawater through young oceanic crust, the seawater emerging enriched with minerals dissolved from the hot rock, those minerals precipitating on contact with cold seawater to build chimneys of metal sulfide and to produce the characteristic dark plumes that gave black smokers their name. Lost City fit a different model. The heat that drove its circulation was not primarily magmatic. It came instead from a chemical reaction between seawater and the mantle rock of the Atlantis Massif, a reaction that generates heat on its own without requiring a magma chamber nearby, and that produces very different fluid chemistry. The chimneys were built not from metal sulfides but from carbonate minerals, aragonite, calcite, and related compounds, pale and slowly growing, surviving for much longer than the geological brief lifespans of most black smoker chimneys. The fluid that emerged from them was not the highly acidic, mineral-laden fluid of a black smoker, but something alkaline, rich in hydrogen and methane, moving slowly upward through mineral walls that the fluid itself had helped to build. Lost City was, in ways that took years to fully recognize, a different kind of thing entirely. It did not replace the existing picture of hydrothermal vents. It expanded it. The discovery of a major, active, geologically unique vent field, only 15 kilometers from the Mid-Atlantic Ridge spreading center, in comparatively shallow water, on a non-volcanic substrate, driven by chemistry rather than direct magmatic heat, suggested that the inventory of vent types was not yet complete. If a field like Lost City had gone unnoticed until the year 2000, the question of what else might be out there along the vast unexplored stretches of the ridge system became considerably more open. The Atlantis Massif had been geologically mapped before Lost City's discovery. Its broad shape, its depth, its location relative to the ridge, these were known in outline. What was not known was that across its summit, for an area of several hectares, a field of carbonate chimneys had been quietly building and venting for a very long time. The mapping tools available before the expedition that found it were not fine-grained enough, or were not directed at that particular part of the massif, or both. The field was present. It was not invisible. It had simply not yet been visited. This is the condition of most of the deep sea floor. Not hidden in any dramatic sense, not protected by any unusual obstacle beyond depth and pressure and the enormous cost of reaching it, simply unvisited, present, available in principle, waiting for the instruments to be pointed at it. In the years since its discovery, Lost City has been revisited multiple times. Each expedition has returned with new data, new samples, new images. The field has been mapped more precisely. The tall white chimneys have been examined up close, their surfaces sampled, their interiors described. The chemistry of the venting fluid has been analyzed. The biology of the organisms living within and around the carbonate walls has been studied at levels of resolution not available in 2000. But the basics of what Kelly's team found in December of that year remain in place. A field of pale chimneys on a shallow underwater mountain, warm alkaline fluid rising through carbonate walls into cold, dark water, a community of living organisms sustained by that fluid and its chemistry. The mid-ocean ridge system continues for 60,000 kilometers around the planet. Along the East Pacific Rise, the spreading is fast and the heat is intense, and the black smoker fields that have been found there are among the most thermally active places on the seafloor. Along the slower spreading sections, the Mid-Atlantic Ridge, the slower zones of the Indian Ocean Ridge system, the ridge sections that thread through the Arctic, the character of hydrothermal activity differs, the chemistry differs, the biology differs. The structures that vents build in slower spreading environments are not the same as those that fast spreading produces. 700 fields identified, 60,000 kilometers of ridge. The mathematics of what remains unvisited is not difficult to feel, even without performing it precisely. There are sections of the ridge system that have been mapped by sonar, but never visited by any camera. There are sections where the sonar resolution is coarse enough that a field the size of Lost City could sit undetected. There are sections in remote parts of the ocean basins, the southern Pacific, the deep Arctic, the Indian Ocean's longer reaches, where the density of expeditions has been thin and the coverage correspondingly sparse. The ridge runs under ice-covered Arctic waters where surface ships cannot easily operate. It runs through ocean regions far from any research institution's home port, where the cost of conducting a cruise is prohibitive for most programs. All of it, seen or unseen, continues. The tectonic spreading goes on. The new crust forms and cools and cracks. The seawater finds the cracks and descends. The heat of the planet's interior warms the water from below. The transformed fluid rises. Along all 60,000 kilometers, in the dark and the cold and the pressure, the same slow cycle is turning, the same cycle that has been turning since the ocean floors formed, since the tectonic system reached its current configuration, since the Earth settled into the dynamic state that it has maintained across most of its history. Some of what rises from those unknown stretches of ridge may be similar to what has already been described. Some of it may be different enough to require new categories. The history of vent science since 1977 is largely the history of each new discovery, expanding the picture beyond what the previous discoveries had prepared scientists to expect. The first vent fields were a surprise. Lost City was a surprise. The discovery in 2016 of an active vent field on the Atlantis Bank in the Indian Ocean, another block of uplifted mantle rock, another site of possible serpentinization-driven activity, extended the picture again. The picture is not finished, but tonight, the picture can rest where it is, along the unbroken chain of underwater mountains that winds around the planet in the dark, along ridges that have been building new seafloor since before the first complex organisms evolved, through basins where the water is nearly freezing and the pressure is enormous and the darkness has no bottom. Somewhere along those 60,000 kilometers, in water no instrument has yet reached, and no light has yet touched, a vent field may be standing, its chimneys built, its fluid warm, its cycle running as it has been running for thousands or tens of thousands of years, in a place so far from the nearest surface ship or research institution that it will be years or decades or longer before a camera descends close enough to see it. The mountains are there. They run without interruption, in the dark below the dark, beneath miles of cold pressing water. They run beneath the South Atlantic and the North Atlantic and the Pacific and the Indian Ocean and the smaller basins that connect these larger bodies. They have been there for a long time. They will be there for a long time more. No surface disturbs the water above them now. No ship crosses every part of them tonight. They are simply present, as they have always been present, in the old dark of the ocean floor, the longest continuous range of mountains on the planet, running quietly around the whole of it, most of them still unvisited, most of them carrying whatever they carry in silence, in the permanent cold, in the permanent dark, in the deep, at the top of a black smoker chimney where the vent fluid meets the open ocean. A mineral is forming. It forms in less than a second. The superheated fluid arrives carrying iron and copper and sulfur dissolved under pressure, and the moment it contacts the surrounding water that sits near freezing at this depth, those minerals crystallize out of solution almost faster than the eye could follow. Layer by microscopic layer, in the dark, the chimney builds itself from what the earth is shedding. The fluid that exits a black smoker vent can exceed 350 degrees Celsius at the orifice. It does not boil, because the pressure at this depth is several hundred times greater than the pressure at the surface. And under that weight of water, the boiling point climbs far above anything familiar. The fluid arrives as a dark, billowing column, not black from soot, but black from iron and copper sulfides, precipitating the instant they meet the cold, and that column rises upward through the water in a slow, dense curl, dispersing outward as it cools, releasing a constant fine mineral rain that drifts down around the base of the chimney and settles into the sediment. The plume is not violent. From a distance, it looks like slow smoke from a fire that has been burning for a very long time. The chimney itself is made of that same precipitation, accumulated and accumulated again over years and decades. The walls are dark and rough, metallic in places, streaked with iron sulfide minerals that catch the submersible's light and give it back in dull bronze and gray. In some sections, the walls look almost industrial, as though something had manufactured them. They are, in a sense, manufactured by chemistry, by pressure, by the meeting of two water masses at opposite ends of the temperature scale. Each layer represents one more pulse of superheated fluid arriving at the surface, one more instant of crystallization, one more fraction of a millimeter added to a structure that may be several meters tall and several decades old. Inside the chimney wall, the temperature gradient is extreme. The fluid at the very center of the vent shaft runs above 350 degrees. At the outer wall surface, the water is close to 2 degrees Celsius. Within a distance no longer than a human hand, that temperature slides across a range broader than the distance between boiling and freezing at the surface of the earth. This is not a smooth gradient. It is irregular, folded by the structure of the mineral wall, divided into pockets and channels and crevices where different temperatures hold. The result is a mosaic. A dozen different thermal zones exist within a space that could fit on a tabletop, each one a distinct habitat, each one occupied accordingly. The minerals that fall from a black smoker's plume carry iron and copper and zinc in their crystalline structure. Where they accumulate thickly around the vent base, they form mounds of sulfide ore, dark and heavy, slowly building from the seafloor upward. Over geological time, These mounds can grow large enough to constitute significant mineral deposits, though, at the time scale of a single human life, they appear fixed and still. The chimney above them looks permanent, but it is not. Black smoker chimneys can collapse and be rebuilt. They can be abandoned when the fluid pathway beneath them shifts. A new crack opens in the crust, and the vent moves, and the old chimney cools and becomes a dark mineral column, standing silent in the dark. The chemistry that drives a black smoker is the chemistry of magma. Seawater percolates down through cracks in the oceanic crust, traveling sometimes several kilometers into the rock before the heat of the underlying magma takes hold of it. The water is stripped of its oxygen and enriched with minerals leached from the surrounding rock at high temperature. Then it rises. The buoyancy of heated water drives it upward through whatever fractures allow, and it arrives at the seafloor, changed, carrying iron, carrying sulfur, carrying zinc and copper and manganese, carrying heat enough to strip taint from any surface that could survive the pressure and the dark. Not all of the ocean floor's vent systems run on magmatic heat. Several hundred miles off the mid-Atlantic ridge, at a depth between 700 and 900 feet below the surface, shallower by far than most vent fields, there is a place where the chemistry runs entirely differently, and the chimneys it builds are white. The Atlantis Massif is a broad, flat-topped underwater mountain raised from the Atlantic seafloor by geological forces that brought deep mantle rock upward through the crust. Its summit sits close enough to the surface that it is shallower than many known vent fields, though still far below any light. On and around this mass, in December of the year 2000, a research team found something that had not been predicted: a field of pale carbonate chimneys rising from the rock in clusters, some of them reaching heights that dwarfed anything that had been built by sulfide precipitation. They named the field Lost City. The chimneys of Lost City are white, or nearly so, ivory in places, gray-white in others, with surfaces that have been described as resembling coral, or the close-packed florets of a cauliflower, textured and rounded and organic in appearance, though no animal grew them. They are built from minerals called aragonite and calcite and brucite, carbonate compounds that precipitate from warm alkaline fluid as it meets the surrounding cooler water, forming slowly over thousands of years rather than in the rapid crystalline bursts that build a black smoker's walls. The structure they produce is different in character. Where a black smoker chimney looks dense and metallic, a Lost City chimney looks almost biological, pale, irregular, grown rather than deposited. The tallest known chimney at Lost City stands approximately 60 meters, nearly 200 feet from base to tip, rising through the dark water in a single column that narrows as it climbs. It is called Poseidon. At 60 meters, it is taller than many buildings, built entirely from minerals that the ocean floor has slowly exhaled. Its surface is not smooth. It is layered and nodular, crusted with carbonate formations that have built up over a span of time longer than any recorded human civilization. The fluid that moves through it and emerges from its tip is not the violent superheated jet of a black smoker. It is a slow, warm seep, perhaps 40 to 90 degrees Celsius at the vent opening, far below the temperatures at a magmatic vent, rising in a gentle shimmer that only becomes visible where the thermal difference between the vent fluid and the surrounding water bends the light passing through. The process that drives Lost City is called serpentinization, and it does not require a volcano. It does not require any magmatic activity at all. It requires only seawater and the right kind of rock, the iron and magnesium-rich mantle rock, called peridotite, which makes up the deeper layers of the ocean crust and the mantle beneath it. When seawater contacts peridotite and a related mineral called olivine, a chemical reaction begins that transforms the rock into a new mineral called serpentine. This transformation releases heat, it releases molecular hydrogen, it releases methane, and it releases it all without any external heat source, because the reaction itself generates the warmth that sustains it. The serpentinization reaction is self-reinforcing in a way that takes time to understand. As seawater reacts with olivine, the rock changes structure and expands. The expansion fractures the surrounding rock. New fractures mean new surfaces of fresh olivine exposed to circulating water. Those new surfaces react and expand and fracture more rock and expose still more olivine. The reaction propagates through the rock over decades and centuries, slowly consuming the peridotite from the outside inward, converting it to serpentine while steadily producing hydrogen and heat. There is no central fire. There is only the chemistry of water meeting rock in the slow dark below the seafloor, sustained by the geometry of its own products. The heat released by serpentinization is real and measurable, but it is different in kind from the heat of magma. A black smoker is connected to a heat source that can run to thousands of degrees in the rock below. The heat of a planet's interior, the heat of tectonic motion and partial melting. Serpentinization is cooler. The reaction produces temperatures that can sustain venting in the range of 40 to 90 degrees Celsius at the outlet, sometimes higher in especially active zones, but not the 350 degrees or more of a magmatic vent. The vent field that results is warmer than the surrounding ocean, but not violently so. It is a persistent, gentle warmth, maintained over timescales that seem almost geological in themselves. The fluid that emerges from a lost city vent is alkaline, strongly so, with a pH that can reach 11 or higher. This is far above the neutral value of 7, far above the slightly acidic pH of the surrounding deep ocean water. The alkalinity comes from the serpentinization chemistry, which generates hydroxide ions as a byproduct of the olivine to serpentine conversion. The resulting fluid is rich in hydrogen, rich in methane, warm and highly alkaline, a chemistry quite unlike the acid sulfide-laden fluid of a black smoker, and one that supports a very different set of processes in the rock and water around the vent. The white minerals of a lost city chimney precipitate because of the contrast between the alkaline vent fluid and the cooler, slightly acidic seawater it enters. Where the two fluids meet, calcium and carbonate ions combine and fall out of solution as aragonite and calcite. The reaction happens slowly, relative to the near-instant sulfide precipitation of a black smoker. The carbonate crystals that form are finer, the textures they create more intricate and organic-looking, the structures they build over time more massive and enduring. A black smoker chimney may grow quickly and collapse. A lost city chimney grows over millennia and stands for tens of thousands of years. Poseidon itself has been venting for an estimated time spanning tens of thousands of years. This is not a number that carries easy weight in ordinary terms, so consider what it means in the language of the human world. When Poseidon began building its current structure, the ice sheets of the last glaciation still covered large portions of the northern continents. The sea level was lower. Humans existed, but the oldest known cities did not. Agriculture had not yet been invented. And through all of that time, through the retreat of the ice, through the flooding of coastlines, through the slow accumulation of everything human beings have built and lost and rebuilt, the Poseidon chimney was here, in the dark, in the water, venting. The fluid moving through Poseidon right now has been in the rock for a long time before it arrives at the chimney. Water percolates slowly through the fractured peridotite of the Atlantis Massif, following whatever pathways the serpentinization reaction has opened over the centuries. It absorbs hydrogen, it absorbs methane, it warms, and then it rises. Not quickly. This is not a violent expulsion, but a slow, pressure-driven seep, and it arrives at the chimney and moves through the carbonate walls and emerges at the tip in that quiet thermal shimmer, carrying its chemistry upward into the water column above. The carbonate minerals that make up the chimney walls are porous. This is important and worth slowing down to consider. The walls of a lost city chimney are not solid in the way that a concrete column is solid. They are more like a sponge, a rigid mineral sponge, full of channels and pores of varying sizes, some large enough to see without magnification, others far too small. Through these pores, the vent fluid moves. It seeps through the interior of the chimney on its way from the interior of the rock to the open water above, and as it moves, it encounters the cold ocean seeping inward from the outside surface. The two fluids meet inside the chimney wall, not just at the tip. The entire porous structure is a meeting place for the chemistry of the deep earth and the chemistry of the ocean, a diffuse and intimate mixing that happens across the full surface area of the mineral structure. The outer surface of a lost city chimney in an active section of the field is coated in a white film, sometimes thick, sometimes thin, always continuous, that covers the carbonate like a skin. This film is alive, but describing what lives within it belongs to another part of the account. What matters here is its appearance and its position, a soft pale layer resting on the pale mineral surface in the dark water, neither the rock nor the ocean, but something that has grown between them. At the base of the chimneys, where the carbonate structure meets the bare rock of the Atlantis Massif, the field spreads outward in low mounds and irregular formations, not as tall as the great chimneys, but covering more ground. Some of these formations are actively venting. Others have gone quiet, cooled, no longer connected to a live serpentinization front below. The dead formations are still white, still standing, but their surfaces are crusted differently, less fresh-looking, the pores partially sealed by continued mineral deposition that has slowed from the inside rather than building outward. The active and inactive sections of the field sit close together. A few meters may separate a vent that has been flowing for thousands of years from a structure that has been cold for a century. In the dark from a distance, they look identical. The Atlantis Massif itself is the reason Lost City exists where it does. The massif formed through a process called an oceanic core complex, a geological event in which the crust extended and thinned along a detachment fault, causing a dome of deep mantle rock to be exhumed and lifted toward the sea floor. This brought vast quantities of peridotite, the rock that serpentinization requires, into contact with seawater at depths and temperatures that allowed the reaction to proceed. The massif is wide and flat-topped, its summit sitting at roughly 700 meters depth, well above the typical 2,000 to 2,500 meters of most mid-ocean vent fields. This shallower position is part of why Lost City sits at the depths it does, and why its chemistry behaves differently from vents deeper along the ridge. Black smoker systems and alkaline vent systems like Lost City are not simply two variants of the same process. They are products of different geological settings, different source rocks, and different heat regimes, producing fluids with almost opposite chemical characters. A black smoker fluid is hot, acidic, and rich in metal sulfides. A Lost City fluid is warm, highly alkaline, and rich in hydrogen and methane. The minerals that precipitate from each are different. The temperatures at the orifice are different. The structures that accumulate are different in height, color, texture, and composition, and the timescales over which each persists differ as well. Black smokers can be short-lived on geological time, dependent as they are on the shifting pathways of magmatic systems, while a serpentinization-driven field like Lost City can sustain itself as long as fresh peridotite remains in contact with circulating seawater, which may be for millions of years. More than 700 hydrothermal vent fields have been identified or inferred across the 60,000 kilometers of mid-ocean ridge that encircles the planet. The faster spreading ridges, the East Pacific Rise, spreading at several centimeters per year, host primarily black smoker systems because the higher spreading rate produces more frequent magmatic activity and more thermally intense fluid circulation. The slower spreading ridges, including the Mid-Atlantic Ridge, which spreads at roughly 2 centimeters per year, more commonly produce the conditions that favor serpentinization, because slower spreading exposes more mantle peridotite at the seafloor through the tectonic detachment faults that formed the Atlantis Massif. Lost City sits on a slow ridge. It is in part a product of slowness. The thermal gradient at a black smoker vent deserves one more moment of attention because it is one of the more extreme physical gradients known anywhere in nature, accessible to direct measurement. Stand the width of a human hand, perhaps 20 centimeters, across the orifice of an active black smoker. At the center of the orifice, the fluid is above 350 degrees Celsius. At the outer edge of that same hand width, in the ambient deep ocean water, the temperature is near 2 degrees. That gradient, 350 degrees across 20 centimeters, is steeper than the gradient between a campfire and the cool air 1 meter away. It is steeper than the gradient from the surface of a star to its immediate atmosphere at equivalent distances. It is, at the scale of centimeters, one of the most extreme thermal boundaries on the planet, and it exists in total silence, in total darkness, at a pressure high enough to compress most gases into strange, dense states, and it has been there, in one form or another, at one vent or another, for as long as the mid-ocean ridges have existed. Brucite, one of the 3 primary minerals in a Lost City chimney, is a magnesium hydroxide compound. It is softer than aragonite and calcite, more soluble in the surrounding seawater, and tends to dissolve faster from the outer surfaces of exposed chimney walls, while the harder carbonates remain. This differential dissolution shapes the surface texture of the chimneys over time, wearing away the brucite-rich zones and leaving behind the harder calcite and aragonite in irregular protrusions and ridges. The cauliflower texture that has been described from Lost City's chimney surfaces may in part be a product of this differential weathering, the softer mineral retreating, the harder mineral standing in relief, the whole surface taking on a sculpted quality over the long span of its existence. The thermal shimmer from a Lost City vent is not easy to see in ordinary lighting. Because the fluid is warm rather than violently hot, the temperature difference between it and the surrounding water is smaller than at a black smoker, and the resulting refraction of light passing through the mixing zone is subtle. Submersible cameras capture it as a slight wavering in the image, the way distant pavement shimmers on a hot day, translated to the cold dark of the deep ocean. The shimmer is visible most clearly when viewed across the line between the vent fluid and the ambient water at an angle that exaggerates the optical distortion. Directly above the chimney tip, looking down the column of rising fluid, it can be nearly invisible. The methane that serpentinization produces is an interesting byproduct to sit with for a moment. Methane is a simple molecule, one carbon atom bonded to 4 hydrogen atoms, and its presence in vent fluids was noted early in the study of Lost City as one of the distinguishing features of the alkaline vent chemistry. Methane is produced abiotically here, meaning without any biological involvement, by reactions that may have been running on the early Earth long before any organism existed. The methane rises with the vent fluid and enters the water column, where it drifts and disperses. Some of it reaches the overlying water, some of it is consumed, and some of it may do other things, in circumstances and at scales that the present record of study only partially illuminates. The hydrogen that serpentinization produces reaches concentrations at Lost City that have rarely been matched in any other natural hydrothermal system measured so far, at 15 millimoles per kilogram of fluid, a concentration that would be vanishingly small in ordinary terms, but is extraordinary by the standards of dissolved gas in deep seawater. The hydrogen of Lost City's vent fluid represents a supply of chemical energy so concentrated that it sustains processes running at every scale, from the molecular to the ecological. The hydrogen diffuses through the pores of the chimney walls. It enters the fluid moving through the rock. It rises through the carbonate structures and enters the water column and disperses on slow currents. Where it goes and what it encounters along the way is a story told in chemistry, in the slow grammar of molecular interaction, unfolding in the dark. The field of Lost City covers an area of roughly 5 acres on the summit and upper flank of the Atlantis Massif. Within that area, the distribution of active and inactive venting is uneven. The tallest and most vigorous structures cluster in one area. Lower, quieter formations spread outward. Beyond the edge of the active field, the rock is bare, cold basalt and peridotite, no carbonate buildup, no visible indication that anything is happening below. The transition from the active vent field to the surrounding seafloor is not gradual. It has edges. One part of the massive surface is covered in pale carbonate formations. A few meters away, there is nothing. The Poseidon Chimney is the largest and oldest of the active structures at Lost City, but it is not unique in its age. Several other large formations at the site have been dated by uranium-thorium methods to ages spanning tens of thousands of years. The dating tells researchers not just how old the structures are, but how long the serpentinization reaction has been active in the rock beneath, because a chimney can only grow as long as warm, mineral-carrying fluid continues to move through it. A chimney that is 50,000 years old represents 50,000 years of continuous reaction in the rock below. The reaction began before Poseidon's first carbonate crystal formed, in rock that seawater had only recently begun to infiltrate, and it has continued without pause since then, building the chimney one slow layer at a time, while the world above went through glaciations and warmings, and the slow accumulation of human history. Mid-ocean ridge segments that host serpentinization-driven vent fields are not distributed evenly around the planet. They tend to concentrate along the portions of the ridge system where mantle rock is most accessible, where the thin oceanic crust has been stretched or faulted in ways that bring peridotite close to the seafloor. The Mid-Atlantic Ridge has several known regions where this occurs. The Indian Ocean Ridge System has others, and there are portions of the Pacific and Arctic ridges where serpentinization may be occurring at depths and in configurations not yet fully documented. The global picture of alkaline vent systems is still being assembled, slowly, by researchers working at the edges of what remotely operated vehicles and autonomous instruments can reach. A black smoker chimney in active venting can grow several centimeters in a day under the right conditions. A Lost City carbonate chimney grows at a fraction of that rate. The slow precipitation of aragonite and calcite from mildly warm alkaline fluid accumulating over years rather than days. The difference in growth rate is a direct reflection of the difference in the chemistry and temperatures involved. Fast growth from high temperature, high concentration fluid, slow growth from warm, diffuse alkaline fluid. The result is that a black smoker chimney can be built and destroyed in a human lifetime, while a lost city chimney outlasts every human structure ever built, silently accumulating mass in the dark, indifferent to time in the way that geological processes are indifferent, not because they are unaffected by it, but because they operate at scales where the difference between a year and a century is not meaningful. The carbonate walls of an actively venting lost city chimney are warm to the touch, not hot, not burning, but warm in the way that a rock left in the sun is warm, except that here the warmth comes not from above, but from within. The fluid moving through the pores carries the heat of the serpentinization reaction upward from below, and the wall conducts some of that heat outward into the surrounding water. Around an active chimney, the water temperature is slightly elevated for some distance, a few meters perhaps, before it merges back into the near-freezing ambient temperature of the deep Atlantic. This thermal halo is too small and too gentle to detect without instruments, but it is there, a soft circle of warmth in the cold dark surrounding the chimney on all sides. The fluid that has moved through the interior of the Poseidon chimney and emerged at its tip tonight is already mixing with the seawater above the field, rising in a slow thermal plume that disperses upward and outward. Some of it will drift for many kilometers before all trace of its vent chemistry is lost in the surrounding ocean. Some of the hydrogen it carries will be consumed before it has traveled far from the chimney. The methane will persist longer, drifting with the current, and the warm water of the plume will cool as it rises, losing its buoyancy, merging with the deep Atlantic in slow, invisible layers that mix over weeks and months until nothing distinguishes them from the water around them. The vent will still be there. It will still be producing that fluid, and the plume will be rising again by the time the previous one has fully dispersed, a continuous emission that has not stopped for tens of thousands of years and shows no sign of stopping. The Atlantis Massif sits in darkness now, as it sat in darkness before the first research vessel came to this part of the Atlantic, as it sat in darkness before there were research vessels, before there were oceans full of ships, before there was anyone to wonder what lay at the bottom of the sea. The peridot, in its core, has been reacting with seawater since the massif was first lifted toward the sea floor. The serpentinization has been running, the hydrogen has been rising, the carbonate has been settling into pale layers around the chimneys. Poseidon has been venting since before the last ice receded from the northern plains. All of this has been happening in the dark, without observation, without record, continuous, patient, unhurried, as the slow transformation of rock to mineral, to water to mineral again. The chemistry does not require a witness. It does not require anything but the rock and the water and the depth of time in which they have been meeting, and it will continue long after every surface instrument has gone quiet, down in the dark at the summit of a seamount in the middle of the Atlantic, building one more layer on a chimney that was old before the first city stood. At 800 feet below the surface of the Atlantic Ocean, there is no day. There never has been. The light that enters the water from above fades in stages, first the reds, then the oranges, then the last thin violet thread, and by the time a diver reaches 200 feet, the world above has become a dim blue memory. Deeper than that, even the memory is gone. What remains is not merely darkness in the way a room is dark when the lamp is switched off. It is the complete and permanent absence of every photon that has ever touched a plant, warmed a shore, or drawn a shadow. It is darkness that is not waiting to end. And inside that darkness, on the white carbonate surface of a chimney that has been standing for longer than any human civilization, something is eating. Not eating with a mouth, not eating in any way that would be visible to the eye, but eating nonetheless, pulling energy from the mineral world, converting it into the chemistry of living tissue, building itself and its neighbors, and the whole quiet community of this sunless place from nothing more than hydrogen and carbon and the warmth leaking out of rock. This is metabolism. This is life. And here, at a place called Lost City, it runs without any reference to the sun at all. The idea that life required light was not a belief anyone held consciously. It was assumed in the way breathing is assumed, a background condition so fundamental that no one had occasion to think about it. The entire visible living world is built on photosynthesis, in one form or another. The grass in a field captures sunlight and stores it as sugar. The deer eats the grass, the wolf eats the deer. The bacterium in the soil breaks the wolf down after it dies, and the carbon returns to the air, and the grass draws it in again. Every step in that chain traces back to a green cell on a sunny surface, gathering light. That was, until fairly recently in the history of science, what energy for life meant. Down here, none of that applies. The chain does not reach this depth. What falls from the ocean's surface, the slow, soft drift of dead organic matter that ocean scientists call marine snow, does reach the seafloor in most places, carrying trace amounts of sunlight energy captured far above. But at Lost City, the chemistry of the vent fluid is so unlike the surrounding seawater, and the microbial community is so thoroughly organized around its own local chemistry, that very little of what filters down from above matters. The living world here is closed. It runs on its own fuel. It does not wait for what the sun sends down. The chimneys of Lost City rise from a broad, flat-topped undersea mountain in the Atlantic, roughly 15 kilometers west of the ridge where the American and Eurasian tectonic plates slowly pull apart. The mountain itself, called the Atlantis Massif, is made of a kind of rock that rarely appears at the sea floor, mantle rock, dense and dark, called peridotite, which normally sits far deeper than the ocean bottom, but was lifted here by the same slow tectonic movements that are still reshaping the ridge. When seawater seeps down through the cracks in this rock, something happens that does not require a magma chamber or a volcanic hotspot. The water and the rock begin to react. They change each other. The minerals in the peridotite absorb the water and transform into a new mineral called serpentine, and in doing so they release heat and they release hydrogen gas, and they alter the chemistry of the water that moves through them until it becomes warm and alkaline and rich with dissolved gases. That altered water rises again, slowly, through the interior of the mountain, and where it finds an opening at the surface, it vents. The chimneys grow from the minerals the fluid carries, precipitating from the rising alkaline water into pale white and cream-colored carbonate towers, some of them as tall as a 6-story building, their surfaces soft and textured and continuously wet with the slow seep of warm fluid. The tallest of these, a structure called Poseidon, has been venting for tens of thousands of years. Its surface has a texture that field researchers have compared to cauliflower, rounded, layered, organic-looking despite being entirely mineral. Fluid drifts upward from its openings, not in jets but in slow, shimmering wisps, the way heat rises off warm pavement on a still evening, visible only by the slight distortion it creates in the water above. And across every surface of this chimney, across the pores and channels and flat ledges of its pale carbonate walls, an invisible community is at work. The organisms that live on these chimney walls are archaea, a domain of single-celled life distinct from bacteria, though easy to confuse with them in casual description. Archaea are ancient. Their lineage reaches back to the earliest chapters of life on this planet, and their chemistry is in several ways unlike anything in the other two great domains of life. The membranes that enclose archaeal cells are built differently. The molecular bonds that hold them together are structured in a way that resists heat and extremes of chemistry more effectively than the membranes of bacteria or the cells of more complex organisms. This is not an accident of their history. It is why so many archaea are found in places where the conditions themselves would dissolve or denature ordinary cellular machinery. At Lost City, one group of archaea dominates. In samples taken from inside the chimney walls, in the deepest and warmest interior channels where the vent fluid is most concentrated, a single lineage of methane cycling archaea can account for more than 9 out of every 10 cells present. This group belongs to an order known from other extreme environments, but has developed at Lost City specifically into a form so well adapted to the local chemistry that researchers gave it its own designation, the Lost City methanosarcinials, named for the place that shaped them. They are not large, they are not visible. Under a microscope, they appear as small rounded or irregular forms, unremarkable to look at. But their metabolism, running quietly in the warm, dark interior of a carbonate chimney on the Atlantic seafloor, is one of the most ancient forms of energy use that biology has so far found. What they eat is hydrogen, or more precisely, what they use is the chemical energy available when hydrogen reacts with carbon dioxide, a reaction that produces methane as a byproduct, and that releases just enough energy to drive the biochemical machinery of a living cell. The hydrogen itself comes from the rock. It is a product of the serpentinization reaction, the water rock chemistry that built the chimney in the first place and continues to run in the depths of the Atlantis Massif, far below the chimney base. That reaction releases molecular hydrogen in quantities that, in the fluid venting from Lost City, reach concentrations among the highest ever recorded in any natural hydrothermal system. The rock is, in this sense, the first link in a food chain, not a plant, not a photosynthetic cell, not anything that we would ordinarily recognize as a producer, but a geological process producing a reduced molecule that a living organism can extract energy from. The methane that the archaea produce as they consume this hydrogen does not simply vanish. It becomes, in turn, a substrate for other organisms. Some archaea can reverse the process, oxidizing methane rather than producing it, running the chemistry in a different direction and extracting a different increment of energy. Sulfate-reducing microbes use the hydrogen or the methane alongside sulfate dissolved in the seawater and pull their energy from that reaction instead. Each metabolic community inhabits a slightly different chemical niche within the chimney, and in doing so, each one creates the conditions for the next. The byproduct of one group's metabolism becomes the fuel for another's. The system cycles. It is not efficient in the way an engine is efficient. Energy is lost at every step, as it always is, but it is sustained, and it is continuous, and it has been running at Lost City for a very long time. The walls of the chimneys are not uniform. Seen in cross-section, in cores taken from chimney samples brought back to the laboratory, they reveal themselves as layered and structured, organized not by any plan, but by chemistry. On the outer surface of a chimney, where the carbonate wall meets the cold surrounding seawater, oxygen is present. Cold, deep ocean water carries dissolved oxygen, and where it touches the chimney, aerobic microorganisms can live. organisms that use oxygen in their metabolism the way the cells of most familiar living things do. These outermost communities are thin, constrained by the limited supply of both oxygen and chemical fuel at that boundary. A little deeper into the wall, where oxygen no longer penetrates and the chemistry shifts toward the alkaline warmth of the vent fluid, different organisms take over. Here the methane cycling archaea are most dense, the hydrogen concentrations are higher, the temperature is warmer, and the chemistry is closer to what the vent fluid itself carries. This is the zone of maximum activity. Deeper still, in the innermost channels where the fluid moves most directly from the rock below, conditions become more extreme, warmer, more alkaline, richer in hydrogen, and the community shifts again toward organisms tolerant of the most demanding conditions. This vertical layering in a chimney wall mirrors, in miniature, the way microbial communities organize themselves in soils and sediments on the surface of the earth. Each layer processes the chemistry that the layer above it leaves behind. Each metabolic community modifies its environment in a direction that the next community finds usable. It is a self-organizing system, not guided by any coordination between its members, but falling into order the way cream falls through coffee, each part following the chemical gradient available to it, the whole settling into a structure that persists. Among the most heat-tolerant organisms known anywhere on Earth are certain archaea that live in and around hydrothermal systems. Pyrolobus fumarii, first isolated from a black smoker chimney wall in the mid-Atlantic, can grow at temperatures above 113 degrees Celsius and cannot in fact grow at temperatures below 90 degrees. The heat that would kill nearly every other organism is for this microbe the minimum condition for life. Methanopyrus candleri, found in hydrothermal sediments, was observed growing and dividing at 121 degrees Celsius in laboratory conditions, the highest confirmed growth temperature for any living organism yet studied. These are not organisms living despite their environment. They have been shaped over vast time by that environment, and the conditions that would destroy a cell built of ordinary chemistry are for them ordinary. The enzymes that drive their metabolism are stabilized by additional molecular bonds that prevent them from unfolding in the heat that would denature a normal protein. Their membranes are structured differently, with molecular architectures that remain fluid and functional at temperatures where a standard lipid bilayer would fuse and fail. These are not emergency solutions or stress responses. They are the normal, stable, well-functioning biochemistry of an organism built from the beginning to live where the rock is hot. At Lost City, the vent fluid is considerably cooler than at a black smoker, temperatures in the range of 40 to 90 degrees Celsius rather than 350 or more. But the alkalinity is extreme, and the hydrogen concentrations are high, and the mineral chemistry is its own kind of challenge. The organisms adapted to these conditions are not the same as those at hotter, more acidic black smokers. Each vent system shapes a distinct community, and each community is in some sense a portrait of the chemistry that produced it. There is a question, much older than the discovery of Lost City, about where the first living organisms came from, not where they came from in evolutionary terms, not which organisms gave rise to which other organisms, but how the very first cellular chemistry began, in a world that had no biology yet, from raw materials that were purely geological. This is one of the oldest and hardest questions in science, and no one has answered it fully. But the chemistry of alkaline hydrothermal vents has come to occupy a central place in the best current thinking about what conditions might have made it possible. One part of the answer has to do with membranes. A living cell is at its simplest a compartment, a boundary that separates the inside from the outside and allows a different chemistry to develop within. Without compartmentalization, the molecules of early metabolism would have dispersed into the ocean as fast as they formed, too dilute to react with each other, too scattered to build complexity. Something needed to hold them together. At Lost City, inside the carbonate chimneys, there are microscopic pores and channels in the mineral walls, spaces a few millimeters across at most, often much smaller, through which the vent fluid slowly percolates upward. These pores are not cells. They have no membrane, but they are compartments. They separate an inside from an outside. They concentrate the chemistry of the vent fluid in a small enclosed space. And their mineral walls are not inert. They are catalytic, studded with iron and sulfur compounds that can facilitate the kinds of chemical reactions that early biochemistry might have needed. The connection between the mineral chemistry of a vent chimney wall and the chemistry inside a living cell is not a loose or speculative one. The iron-sulfur clusters that sit in the cores of many of the most ancient enzymes known in biology, proteins involved in electron transfer and carbon fixation in methanogens and acidogens and sulfate reducers, bear a close structural resemblance to the iron-sulfur mineral clusters that form naturally in vent chimney walls. This resemblance has led some researchers to suggest a direct evolutionary relationship, that the first biological catalysts were mineral surfaces, that early chemistry co-opted the geometry of iron-sulfur minerals into its own molecular structure, and that what we now call enzymes are in this deep sense descendants of rock. The carbon fixation pathway used by the archaea at Lost City, a pathway called the Wood-Lungdahl pathway, found also in certain bacteria and considered among the most ancient forms of carbon chemistry and biology, uses hydrogen and carbon dioxide to build organic molecules in a sequence of steps that runs on very little energy and requires conditions not unlike those inside an alkaline vent chimney. This pathway does not use sunlight. It does not require oxygen. It requires the kind of chemically reducing, hydrogen-rich, alkaline environment that serpentinization produces. The fact that organisms still using this pathway today are found in the chimneys of Lost City, that the most ancient-seeming biochemistry is still running in an environment that resembles in its essentials what the early Earth's seafloor might have provided, is not a coincidence. It is a thread, long and quiet, connecting the present to an unimaginable past. Picture the interior of a single chimney pore. It is small, small enough that the width of a human hair laid across its opening would cover it. The walls are pale carbonate mineral, rough and slightly crystalline, and through them the vent fluid seeps in slow infiltration, carrying its hydrogen and its methane and its alkaline chemistry. On the walls of this pore, archaea have settled. They are so small they are invisible at any magnification a human eye could perceive, unaided, each cell a few thousandths of a millimeter across, membrane enclosed, metabolically active in the warm dark. They are consuming the hydrogen that the rock below is producing. They are exhaling methane. They have been doing this in this pore, or one very like it, for a very long time. The methane that drifts out of this pore moves upward through the chimney, and in the cooler, oxygen-touched outer layers of the wall, it may encounter organisms that will use it in turn. Their metabolic byproducts will feed others. The warm fluid that carries everything upward emerges finally from the chimney's surface and drifts into the cold Atlantic above, carrying its dissolved chemistry and its microbial passengers in a slow plume that disperses over the surrounding seafloor seeding new surfaces, finding new mineral edges, beginning the colonization of new territory in the cold dark. The chimney breathes in a manner of speaking. It exhales chemistry that the ocean accepts and carries away. The darkness above the chimney is not total, though it is very close. There are organisms in the deep ocean, jellyfish, fish, squid, that produce their own light through bioluminescence, and occasional flickers of blue-green cold fire move through the water column above Lost City, as they do above most of the deep sea. But this light is brief and local and biological. The vent itself produces no light. The chimney produces no light. The microbial mats that coat every surface glow with no color visible to any eye. The entire chemical feast happening on the walls of these carbonate towers takes place in a darkness that has been unbroken since the mountain rose from the seafloor millions of years ago. This is not incidental. It is the point, the discovery that complex, self-sustaining, highly organized biological communities can exist in complete darkness, powered entirely by chemical energy, changed the understood boundaries of where life was possible. Not in a dramatic way, not as a sudden realization, but as a slow accumulation of evidence, dive by dive, sample by sample, across the years that followed the first vent discoveries. The realization settled rather than exploded, and what settled into place was a picture of life as something more flexible, more chemically versatile, and more independent of solar energy than anyone had assumed. Life did not need a star, it needed chemistry, and chemistry was available in the dark. The mat on the outside of a Lost City chimney is thick enough to have texture, pale, slightly flocculent, soft-looking, continuous across the carbonate surface in the way moss is continuous across a stone wall in a damp forest. It is not moss. It is a dense community of single-celled organisms, most of them archaea, many of them still uncharacterized in any formal scientific sense. Samples taken from this mat and analyzed for their genetic material reveal an extraordinary diversity of lineages, organisms related to each other only distantly, representing metabolic strategies ranging from hydrogen oxidation to sulfate reduction to methanogenesis, all living in proximity on the same mineral surface. They do not cooperate in any way that requires awareness. They simply occupy the niches their chemistry allows, and the chemistry of the chimney provides enough variety of niches that many different metabolisms find a place. The outer surface of the mat is in contact with cold seawater. Its interior is in contact with warm vent fluid. Between these two conditions, across the thickness of the mat itself, which is a few millimeters at most, temperature changes, oxygen concentration changes, pH changes, and the concentrations of hydrogen and methane and sulfate all shift. Each organism in the mat lives in the sliver of that gradient where its particular chemistry works best. The mat is, in this sense, a city, not in the colloquial sense of something grand or organized, but in the functional sense of a dense community where many different kinds of activity run simultaneously in a small shared space, each one sustained by the conditions the others collectively create. Some of the archaea in the Lost City chimneys are capable of surviving conditions that would be described in almost any other context as incompatible with life. The alkalinity of the vent fluid, a pH of 9 to 11, approaching the alkalinity of household bleach, would denature the proteins of most organisms. The near-freezing temperature of the surrounding seawater, just a few centimeters away from surfaces that may reach 90 degrees, creates thermal gradients that most cells could not tolerate. The complete absence of light, the pressure of 700 to 900 meters of water overhead, the chemical specificity of a fluid dominated by hydrogen and methane, any one of these conditions, presented alone to an organism adapted to surface life, would be lethal. And yet the archaea here are not surviving despite these conditions. They are thriving within them. The pH that would strip proteins from most cells is the pH their enzymes are built for. The hydrogen concentration that would be irrelevant or even toxic to many organisms is precisely what their metabolism runs on. The darkness is not a hardship, it is simply the condition. There is a word for organisms that live in extreme environments, extremophiles, but it is worth holding the word loosely, because from the perspective of the organism, there is nothing extreme about the place where its chemistry works perfectly. It is simply home. The methane at Lost City comes from two sources. Some is produced biologically, exhaled by the methane-making archaea as they process hydrogen and carbon dioxide inside the chimney walls. Some is produced abiotically, generated directly by the serpentinization chemistry in the rock below, without any biological step involved. These two sources are chemically almost identical. Distinguishing between them requires careful isotopic analysis of the methane's carbon atoms, since biological processes tend to prefer the lighter form of carbon and leave a slightly different isotopic signature than abiotic chemistry does. At Lost City, both signatures are present. The methane in the vent fluid is part biological, part geological, blended in proportions that shift with depth and temperature and the distance from the most active venting zones. This blending is significant. It means that at Lost City, the boundary between the living and the non-living, between what the organisms produce and what the rock produces, is chemically blurred. The archaea are metabolizing compounds that the rock made. The rock is, in a narrow but real sense, doing chemistry that resembles what the archaea do. Both are running versions of the same basic reaction, one in a cell and one in a mineral matrix, both producing the same molecular output. This is not a philosophical point about the unity of life and matter, though it could become one. It is a chemical observation, specific and measurable, that points towards something deeper about the conditions in which biology first became biology. In a place perhaps not unlike this one, where the rock's chemistry and the first cell's chemistry were not yet fully distinct. The archaea in the Lost City chimneys are not static. Their populations shift with temperature and fluid chemistry, with the seasonal fluctuations in the overlying ocean and the slow tectonic adjustments that alter the flow of vent fluid from decade to decade. When a chimney becomes inactive, when the fluid pathways through the rock below shift and the warm hydrogen-rich water stops rising through its base, the mat on its surface does not die immediately. It persists for a time, drawing on residual chemistry in the carbonate walls, slowly thinning as the gradient flattens and the metabolic substrates are consumed. Eventually, the community fades. The surface cools to the ambient temperature of the deep ocean, and whatever remains of the mat disperses into the surrounding water or settles as organic sediment on the seafloor nearby. A new chimney, somewhere else on the Atlantis Massif, begins to form. Vent fluid finds a new path upward through the rock and emerges at a new opening, and the carbonate minerals begin to precipitate, and the first microbial cells carried by the current, or perhaps surviving in the deep pores of the rock itself, arrive and settle and begin to grow. How long this colonization takes, how far the founding organisms travel, and what determines which metabolic strategies succeed first in a new vent community are questions that field research is still working to answer. The chimneys record their own history in their mineral structure, in the way tree rings record rainfall. each layer of carbonate deposited at a slightly different time, under slightly different conditions, and the record they hold is still being read. At the base of the Atlantis Massif, in the dark sediment between the carbonate towers, the chemistry of the vent fluid mingles with the cold seawater in a zone of gradual mixing. Here the fluid is no longer warm, no longer concentrated, no longer carrying the full chemical signature of the serpentinization reaction above. But even here, in this diluted periphery, microbial activity has been detected. Organisms adapted to lower hydrogen concentrations and cooler temperatures occupy this transitional zone, processing the last residual chemistry that the vent fluid carries before it fully assimilates into the surrounding ocean. The zone of life extends further than the zone of the vent itself. It follows the chemical gradient out into the dark water, thinning gradually, the last organisms occupying the last usable increment of warmth and chemistry before the cold floor of the Atlantic takes over. This gradual fading at the edges of a vent community is one of the things that makes it difficult to draw a clean boundary around what counts as the vent ecosystem and what counts as the surrounding ocean. The two are not separated by a wall. They shade into each other through chemistry and temperature and microbial density, and the exact point where one ends and the other begins is a question of thresholds rather than edges. Life does not stop where the vent stops. It continues until the chemistry is no longer sufficient to sustain it, and that point is somewhere in the cold, dark water between the chimney and the open abyss. The vent fluid that rises through the Poseidon chimney and disperses into the Atlantic carries with it not only hydrogen and methane, but also small amounts of organic molecules, amino acids, and other carbon compounds produced by the archaea as metabolic byproducts or cell components that are shed into the fluid as cells die and break apart. These molecules enter the deep ocean and become part of its dissolved organic matter. They are minute in quantity relative to the ocean's total dissolved carbon load, but they represent something particular: organic carbon produced entirely without sunlight, entering the ocean's chemistry from below rather than from above. In the long accounting of the carbon cycle, this is a small contribution. In the question of how carbon circulates through the deep ocean, it is a real one. The deep ocean is not, in this sense, a passive space, waiting to receive what falls from above. It has its own chemistry, its own microbial communities, its own energy sources that operate independently of photosynthesis. Hydrothermal vents are among the most concentrated expressions of this deep ocean energy, but they are not isolated from the surrounding water. They contribute to it, slowly, continuously, releasing their chemistry into the cold, dark ocean that surrounds them, in a process that has been running since the mid-ocean ridges first formed, and the first alkaline fluids first percolated up through fractured mantle rock. The hydrogen molecule is simple: two atoms of hydrogen bound together by a single covalent bond, carrying no charge, producing no color, making no sound. It is among the most common molecules in the universe, abundant in the gas giants, flung off by young stars, present in the interstellar medium in clouds that span light years. On the surface of the Earth, it is relatively rare in free form. The atmosphere holds almost none, but deep in the rock, where water meets the iron-rich minerals of the mantle and the serpentinization reaction runs, hydrogen is produced. It seeps upward through the fractures in the crust, dissolved in the rising fluid, concentrated in the venting water. And at Lost City, where it reaches the seafloor in the highest concentrations of any vent system yet measured, it becomes the single molecule on which an entire community is built. The archaea do not know they are consuming hydrogen. They do not know anything. They are chemical systems of extraordinary complexity, bounded by membranes, driven by gradients, shaped over enormous time by the pressure of their environment, but they have no awareness of what they do or why. They consume hydrogen because consuming hydrogen releases energy that drives a set of molecular machines that replicates the molecular machines. That is all. That is enough. From this minimum condition, a source of chemical energy, a boundary, a gradient, a replicating chemistry, everything in the vent community follows. The shrimp and the crabs and the tube worms and the fish that live at vents elsewhere on the ocean floor all trace their energy, step by step, back through the food web to organisms like these, running their chemistry in the dark on hydrogen that the rock below produced. The rock does not stop producing it. Serpentinization in the Atlantis Massif has been running for hundreds of thousands of years, perhaps longer. The reaction is self-sustaining in a quiet way. As the olivine in the peridotite transforms into serpentine, the rock expands slightly, cracking along new fracture lines, exposing fresh olivine surfaces to the percolating water, ensuring that new reaction surfaces are continuously generated. The mountain contains vast reserves of unaltered peridotite, and as long as seawater can reach it, the chemistry will continue. The Poseidon chimney has been growing for tens of thousands of years on the energy of this reaction. Its pale carbonate walls hold within their mineral layers the chemical record of every decade and century during which the fluid moved through them, depositing its minerals, coating its surfaces, building upward one slow layer at a time. This is geological patience. This is the tempo at which the deep world operates, not in years or decades, but in the kind of time that erodes mountains and moves continents, measured by the slow accumulation of mineral layers and the equally slow transformation of rock into new rock. The archaea living in the chimneys operate on a different time scale entirely, generations measured in hours or days, populations rising and falling, with shifts in fluid chemistry across weeks or months, but the environment they inhabit operates on the time scale of the mountain, and they are held by it. Their rapid biochemistry runs inside a geological container that barely changes on any time scale they could perceive, if they could perceive anything at all. The warm fluid in the pores of the chimney wall carries the hydrogen upward, and the archaea use it, and the methane they produce drifts further upward, and others use that in turn, and the last residual chemistry disperses into the cold water above. The energy that moves through this chain began in the serpentinization reaction in the rock below, which began when seawater seeped down through a fracture in the sea floor, which began with the pressure of the overlying ocean pushing water into every available crack in the crust. The energy source is ultimately geological, the heat of the Earth's interior, the chemistry of the mantle, the movement of tectonic plates that continues to fracture and expose fresh rock to circulating water. This geological energy entered the biological system without ceremony. There was no moment when the rock's chemistry became life's chemistry, no threshold that was crossed with any visible event. The transition from abiotic to biotic chemistry at hydrothermal vents, if it happened at hydrothermal vents, if it happened at hydrothermal vents, if it happened at hydrothermal vents, which is not certain, but is a serious and well-evidenced possibility, was a gradual dissolution of the boundary between them, chemistry becoming more complex, more self-sustaining, more capable of replicating its own structure, until at some point the system deserved a different name. The archaea at Lost City may be living in something close to the environment where that transition first happened. Their biochemistry echoes it. Their hydrogen comes from the same geological source. Their carbon fixation pathway is the oldest known, and the chimney walls where they live are in their mineral structure and their chemical gradients, a version of the mineral compartments that may have held the first self-replicating chemistry on Earth. None of this is certain. The origin of life is not a solved question. The alkaline vent hypothesis is a strong one, with real chemical evidence and genuine explanatory power, but there are other serious hypotheses, and the conditions of the early Earth are reconstructed rather than observed, and the record of what actually happened has been remade so many times by geological processes that its earliest pages may simply be gone. What can be said is that Lost City provides, in the present ocean, a set of conditions that correspond closely to what the early Earth might have provided: serpentinization-driven chemistry, alkaline fluid, hydrogen-rich environment, mineral compartments, geologically sustained energy, and that the organisms living there use pathways that resembled, in their simplicity and their chemistry, what the first living systems might have used. This is not a claim about ancestry. The archaea at Lost City are not ancient organisms, unchanged from the Hadean era. They have been evolving continuously for 4 billion years, as all living things have. What they share with the earliest life is not their lineage, but their chemistry, the same basic reaction, run with more sophisticated machinery, in a setting that resembles the one where the reaction may first have found its way into a cell. In the quiet of the chimney, the hydrogen molecule drifts upward through the warm fluid. It passes through the pore space in the carbonate wall. It meets the membrane of an archaeal cell and is drawn inside. The cell uses it. Methane is produced. The methane drifts on. The cell divides, slowly, and the daughter cells settle onto the mineral wall nearby and begin their own metabolism. The chimney grows by a fraction of a millimeter. The fluid continues to rise. The mountain continues to react with the water that moves through it. The hydrogen continues to be made. Above the chimney, the cold Atlantic holds its darkness and its pressure. The seafloor stretches away in all directions, flat and bare and cold, for miles in every direction. The mid-ocean ridge runs to the north and south, its fracture zones and volcanic peaks rising and falling through the deep water in a slow topography that no surface map has ever needed to show. And here, on this one wide-topped mountain in the Atlantic, warm fluid rises through pale towers in the dark, and a community of ancient chemistry does what it has always done: consumes the hydrogen the rock provides, builds its membranes and its proteins and its daughter cells from nothing more than that, and persists. The hydrogen is enough. It has always been enough. The rock makes it slowly in the dark, and the dark holds it, and life takes it and continues. The red plumes appeared first, before anything else resolved in the light. 2 meters tall, some of them rising from pale tubes anchored to the volcanic rock, swaying without urgency in the slow thermal currents moving up from the seafloor. The plumes were the color of blood, but moved like smoke, soft, continuous, unhurried, opening and closing in the warm fluid, the way something breathes. Nothing about them suggested the cold, bare abyss that surrounded them on every side. They looked, in the beam of the submersible's light, like a garden someone had planted in the dark and then forgotten. These are tube worms. Each one lives inside a rigid white tube. It is built for itself, from chitin, a material similar to what makes up the shells of crabs and the outer casings of insects. The tube is anchored to the rock. The worm does not leave it. From the open end of the tube, when the worm is calm and the water is warm enough that crimson plume extends, a gill-like structure, densely folded, filled with tiny blood vessels running close to the surface. Through those vessels flows the worm's blood, which is an extraordinary thing, because this blood carries not just oxygen, but also hydrogen sulfide, the compound rising from the vent below, simultaneously and without either one poisoning the other. In most animals, hydrogen sulfide is a lethal molecule. It shuts down the same oxygen handling proteins it touches. This worm's blood does something else entirely with it, binds it, separates it, delivers it to where it needs to go, and in this quiet chemical feat, the whole architecture of the worm's life becomes possible. Inside the worm, where a stomach would be in almost any other animal, there is no stomach, there is no mouth either, and no gut. Where digestion would otherwise occur, there is instead a densely packed internal organ called the trophosome, which occupies most of the worm's body cavity and contains, in numbers too great to estimate precisely, bacteria that have taken up permanent residence there. The bacteria do the feeding. They take the hydrogen sulfide the worm's blood delivers, use its chemical energy to fix carbon from the surrounding water, and build the organic molecules the worm's body runs on. The worm, in return, provides the bacteria with shelter, circulation, and a steady supply of both the sulfide and the oxygen they need. Neither organism would survive long without the other. They have been arranged this way for long enough that the worm has lost completely and without remnant the digestive organs that would have allowed it to feed any other way. A colony of these worms covers the seafloor around an active vent in a kind of softly moving thicket. Their tubes press close together, tilted slightly upward toward the warmer water rising from below. Between the tubes, in the narrow spaces where one worm's territory ends and another's begins, other animals move: small crabs, pale fish, the slow shadows of things, using the colony the way a forest is used, as structure and shelter both. The light from the submersible catches the plumes and turns them briefly bright before moving on, and the darkness closes back behind it, like water filling a space. At greater depths along the mid-ocean ridges of the Atlantic, the hot dark columns of black smoker chimneys rise from the seafloor, and the organisms that gather around them look nothing like the worms of the Pacific. The water here is colder away from the vents, the chimneys taller and more dramatic in their mineral output, and the animal that dominates the scene is not 2 meters long, but small enough to hold in one cupped hand. The shrimp arrive in swarms so dense that from a distance they look like a single living surface draped over the chimney walls. Pale bodies, hundreds of them, thousands, pressing against the mineral surface and against each other with what appears to be a kind of urgency. Though urgency implies intention, and these animals have none. They are following gradients. Warm water and chemistry draw them close, and they cluster where those conditions are strongest. These shrimp have no compound eyes in the ordinary sense. The visual organs of most shrimp sit on stalks at the front of the head and resolve the world into detailed images made from hundreds of small lenses. These ones lost that architecture somewhere in their evolutionary past, and in its place, or more precisely, in a location that is not quite where eyes usually sit, they carry 2 broad, flat, reflective patches on their upper surface, oriented toward whatever lies above them. For a long time, the nature of these structures puzzled the researchers who studied them. They are sensitive to light, but the deep mid-ocean is dark. There is almost no light to detect. Almost, but not quite. The vent fluid itself, at the temperatures where superheated water meets cold seawater, produces a faint emission, thermal radiation, and perhaps a small amount of chemoluminescence, a glow too dim for ordinary eyes, too faint to read or navigate by, but detectable by these specialized dorsal patches if those patches are sensitive enough. The shrimp may be orienting to the vent's own light, however faint, keeping themselves in the zone where the chemistry they need is richest, using a visual system built entirely around a source of illumination that has no equivalent anywhere else on the planet's surface. Inside each shrimp's gill chamber, in the protected space where water passes over the respiratory surfaces, chemosynthetic bacteria grow in dense mats. The shrimp cultivates them there, carries them from birth, tends them without awareness of doing so. When the bacteria become abundant enough, the shrimp harvests them, scraping the growth from its own gill surfaces and consuming it. The shrimp feeds on what it grows. The system is closed, self-referential, entirely independent of any organic matter drifting down from the sunlit ocean above. Around these chimney walls, in these swarms of thousands, the entire economy of eating and being eaten runs on chemistry alone. Far from the Atlantic, in the colder deep waters of the eastern Pacific, a different kind of animal sits at the centers of vent communities in a way that is harder to classify. It is called a yeti crab, a name that comes not from any formal taxonomy, but from the dense covering of long silky filaments called setae that coat its claws and much of its body. These setae are white and fine and abundant, and in the submersible's light, they give the crab a pale, soft, almost fur-like appearance against the dark rock. The claws themselves are large relative to the body, held slightly away from the sides, and the crab moves them slowly through the water in a motion that is rhythmic and deliberate, extending them outward and drawing them back over and over in a pace that has something almost meditative about it from the outside. On those setae, bacteria grow. The yeti crab's claws are not just tools for gripping and defense, they are farms. The chemosynthetic bacteria that colonize the dense filaments take up the hydrogen and methane in the vent water and convert it into organic matter, and the yeti crab, in performing its characteristic slow waving motion, moves its claws through the chemically enriched water close to the vent. The motion is a form of cultivation. The wave draws in fluid, passes it over the bacterial growth, oxygenates it, and exposes it to the compounds the bacteria need to metabolize. The crab is farming. It does not know this, has no concept of what it is doing or why, and would continue the motion whether or not a single bacterium lived on its setae. The behavior predated the farming, probably, and the farming assembled itself around a motion that was already there. The result is that the yeti crab carries its food supply on its own body, tending it through movement, harvesting it at intervals, functioning less like an animal hunting prey, and more like a slow gardener moving through a warm space at the end of a long afternoon. In the waters around the South Sandwich Islands, at depths approaching 1.5 miles down, a related species gathers around hydrothermal vents in a way that transforms the seafloor near the vent opening into something almost geological in its density. These yeti crabs aggregate in layers. They stack on each other, bodies overlapping, the crabs at the inner ring closest to the warmth, and the chemical richness pressing outward against the weight of the crabs behind them, while the crabs behind press inward toward the warmth. Counts from submersible camera surveys suggest densities approaching 700 individuals in a single square meter, which is a number that requires no embellishment. It means that the floor near these vents is for some distance not a floor at all, but a moving, layered mass of living animals. Each one is competing for the same resource, proximity to the warm, hydrogen and methane saturated water that the bacteria on its setae need in order to grow. The result is a ring of life around the vent opening, as dense as anything the deep ocean produces, held in place by chemistry and the slow pressure of thousands of bodies, all wanting the same thing. Among the rocks and the animal thickets, along the edges of the communities where the vent influence begins to fade and the water cools toward the ambient temperature of the deep, there are mussels. They appear in clusters along the bases of chimney structures and in low-lying areas where chemical gradients are gentle rather than intense. Their shells are dark, often encrusted with sediment and other organisms, and they look from a distance like ordinary mussels that might be found in a tidal zone on any coast. They are not. Inside their gill tissue, living within the cells themselves in a relationship more intimate than the one the tube worm maintains with its bacteria, chemosynthetic symbionts conduct the same chemistry the rest of the vent community runs on. The mussels breathe water and extract from it not just oxygen, but the hydrogen sulfide or methane or both that their internal bacteria need. They do not move toward the vent. They position themselves near it in early life and then stay, filtering the chemical-laden water and feeding the bacteria that feed them, locked into the rock and into the community for as long as conditions remain stable. And alongside the mussels, and often covering the same rock surfaces in pale expanses, there are limpets and snails of various kinds, small crustaceans picking through the microbial mat for particles of organic matter, brittle stars moving across the sediment on long articulated arms. These animals are grazers and opportunists, and they occupy the vent community the way similar animals occupy the margins of any productive reef or bed, not as specialists bound to the chemistry, but as generalists making use of an unusual abundance. The tube worm, the vent shrimp, the yeti crab, these are organisms that would not exist, could not survive anywhere other than a vent. The limpets and the brittle stars are different. They followed the food. They arrived because the vent community produces, through its chemosynthetic base, more organic matter per square meter than the abyssal plain that surrounds it produces in a year, and animals that can find their way to such a place and tolerate its chemistry will stay. Moving through the outer water above the community, just within the edges of the submersible's light, before fading back into the dark, there are fish. They are long and pale and move with the deliberate, unhurried motion of deep-sea animals that burn very little energy and need to burn very little more. Some of them belong to a group called eelpouts, elongate, soft-bodied, with broad rounded heads and mouths that open wider than the slenderness of their bodies suggests is possible. They do not depend on the vent chemistry directly. They eat the other animals. A crab moved too slowly, a shrimp that drifted from the safety of the swarm, a worm's plume extending a little too far from the tube. These are what the eelpout is waiting for. It moves slowly because it is not in a hurry, and it is not in a hurry because in this particular circle of the deep ocean, where vent chemistry drives a productivity that the surrounding abyss cannot match, there is enough. The community as a whole has a spatial logic. At the center, the vent opening or the chimney structure, the temperature highest, the chemistry most concentrated, and the organisms there are the specialists, the ones for whom this is the only possible world. Moving outward from the center, the temperature falls and the chemistry dilutes, and the specialization decreases incrementally. The organisms at the outer edge are using the vent, but could potentially use other things. Beyond the outer edge, the abyssal plain resumes, flat, cold, dark, and largely empty, supporting only the sparse animal life that can exist on marine snow, the slow rain of organic particles drifting down from the sunlit surface thousands of meters above. The vent community sits in this emptiness, the way an island sits in an ocean, with a defined boundary in a particular interior, and the open water between one vent field and the next is, for most of the organisms that live at vents, an uncrossable distance. This matters for the question of how each community came to be what it is. The tube worm at a Pacific vent and the shrimp at an Atlantic smoker evolved in near complete isolation from each other, separated not by land or by fresh water, but by hundreds or thousands of miles of cold, dark ocean floor where no vent chemistry exists, and no vent-adapted organism could survive long enough to make the crossing. The provinces of vent life, the Pacific communities, the Atlantic communities, the Indian Ocean communities, the deep basins of the Western Pacific, each developed along their own lines, accumulating their own species, their own specialists, their own arrangements of who eats whom and who lives where on the chimney wall. The same basic structure reappears in every province, because the basic structure is dictated by the vent chemistry, which is broadly similar everywhere. But the animals filling the roles are different. What plays the role of primary consumer in one province is a worm, in another, a shrimp, in a third, a crab of a different genus. The architecture recurs, the species do not. This pattern, when phylogeneticists began to examine it closely, when the molecular sequences of vent animals from different ocean basins were compared and the divergence times estimated, produced a picture of evolutionary time that was difficult to make fully concrete. Some of the separations were very old, populations that had at some distant point been connected, perhaps during a period when the ocean floor's geometry allowed a corridor of vent habitats along which larvae could travel, had been cut off long enough to become entirely different species, sometimes different genera, accumulating changes that the raw similarity of their body plans had entirely concealed. The animal that looks like a tube worm in every external particular may be related only distantly to the tube worm found at a vent on the other side of the planet. The names and even the shapes can be misleading. The molecules are more patient witnesses. Among all the body plans at hydrothermal vents, the tube worms remains the one that most immediately registers as improbable. 2 meters long is the upper end. Many Riftia pachyptilla are shorter, closer to a meter or a meter and a half, and even at that size, they are unlike almost any animal a person would encounter in ordinary life. The tube itself is smooth and white and anchored to the rock at its base. The worm inside is entirely enclosed for most of its length, sealed within the mineral structure it has built. Only the plume at the top extends into open water, and even that can be retracted rapidly if a predator approaches. The whole red structure drawing back into the tube in a fraction of a second, the opening closing behind it, leaving only a featureless white cylinder where a living thing had been. When the danger passes, or when the chemical conditions return to the range the worm prefers, the plume reemerges slowly. The red tissue unfolds from the tube opening like a hand opening. It takes its time. Growth rates among tube worms are high for the deep sea, where most organisms grow slowly to match the slow pace of energy availability. Riftia pachyptilla can grow at more than a foot per year under good conditions, fast enough to be measurable across the span of a single research expedition, and this speed is entirely a product of the chemosynthetic efficiency inside the trophosome. The bacteria are productive, and they fix carbon quickly when the chemical supply is steady, and the worm grows quickly when the bacteria are productive. The vent provides a steady supply. And when the vent becomes inactive, when the geological forces that cracked the crust and allowed superheated water to rise shift their attention elsewhere, as they always eventually do, the whole community collapses with it. The bacteria slow, the worms stop growing. The animals that fed on the worms disperse or die. The chimneys cool, and the minerals precipitate at a different rate, and eventually the structures become cold, silent, and bare, inhabited only by the occasional deep-sea generalist picking over the remnants of organic matter still bound in the sediment. The death of a vent is as much a part of the cycle as its birth. Somewhere along the same ridge, sometimes in geological time, not long after one field falls quiet, the seafloor cracks and opens elsewhere, and the superheated fluid begins to rise again in a new location. Larvae of tube worms and vent shrimp and vent mussels drift in the currents between active fields, spending time in the open water column, searching again, not with intention, but following gradients, following chemical cues, following the temperature signals that indicate vent activity for a place to settle. The lucky ones find a new field. They attach, they begin to build. Within years, the new site is colonized. Within decades, it begins to look like the community that was lost elsewhere, because the roles are the same, and the animals that survive long enough to fill them are drawn from the same pool of vent-adapted organisms that have been circulating in the deep ocean since the ridges formed. The oldest vent fields that have been studied in detail are very old. The Lost City Hydrothermal Field, with its pale carbonate chimneys and its alkaline chemistry, has been active for tens of thousands of years by the best current estimates, an extraordinary span for a surface geological feature made possible by the slow and self-sustaining nature of the serpentinization reaction that drives it. The communities that inhabit a system of that age are not transient. They are not camping in a space that will soon be unavailable. They are, within the frame of reference that biological time allows, residents. The microbial mats on the chimney walls at Lost City are ancient in their lineage, deep in their genetic diversity, layered in a way that reflects not just the current chemistry, but the chemistry of centuries of slow drift and change. The animals at the outer edges of such a field have had time not just to arrive, but to adapt, to specialize, to lose the generalist options that arrival requires, and develop the specialist arrangements that long residence makes possible. This slow settling, this accumulation of relationship and specialization over time, is what makes a vent community something more than a temporary gathering of organisms using an available resource. The tube worm without a mouth, the shrimp with light-sensitive organs on its back, the yeti crab that farms. None of these arrangements appeared quickly. Each required generations of change, of selection, of the gradual narrowing of a lineage toward a particular way of being alive in a particular place, until the original generalist, whatever came before, whatever colonized the early vent and found it merely adequate, had become something that could not exist anywhere else. The vent did not make these animals. They made themselves across long time in response to it. By the time the submersible's light finds them and resolves them from the dark, they are already the end of a very long story. The eelpout fish moving through the outer water of the community does not need a symbiont. It does not cultivate bacteria or carry them in specialized chambers. It eats and moves and eats again, and is occasionally eaten in turn by larger predators that visit from the open water. Its presence at the vent is the presence of an animal following abundance rather than chemistry, and yet its body too, over the time its lineage has spent in the deep, has changed toward the deep. The pale coloration, the reduced eyes in some species, the slow metabolism, the tolerance for pressure and cold. The deep sea makes a particular kind of animal, gradually, whether the energy comes from sunlight filtered down through miles of water or from the hot chemistry of the planet's interior, rising up through the floor. The shape converges, the pace slows, the body becomes long and quiet and capable of waiting. There are organisms at vent sites that have not yet been formally named. The diversity of macroscopic vent fauna, more than 700 species described from hydrothermal environments globally, continues to expand with every expedition because the mid-ocean ridge system is long and the areas that have been closely surveyed represent a small fraction of what exists. New vent fields are discovered with each remotely operated vehicle deployment into an unmapped section of ridge. Each new field brings its own community, and within each community, among the familiar shapes of tube worm and shrimp and crab, there are often animals that do not match any described species, close relatives of known organisms, sometimes differentiated by subtle features of morphology or genetics that only become apparent under examination. What appears at first to be a species already known turns out under the molecular analysis to be something else, something that has been living its entire evolutionary history in isolation at a vent field no human instrument had previously visited. The number 700 as a count of described macrofaunal vent species is an undercount. This is not uncertainty about whether more species exist. It is near certainty that they do. Every expedition to a new vent site returns with material for taxonomists. Some of the undescribed species are waiting in collections, preserved in ethanol, documented by camera, not yet formally processed through the nomenclatural system that assigns them a name and a place in the classification of life. The ocean is ahead of the science in this particular way, and probably will remain so for a long time. A vent community viewed from the outside, from the vantage of the submersible hovering a few meters above the seafloor, its cameras recording the chimneys and the organisms around them in the cone of available light, does not look random. It looks composed. The tube worms occupy the mid-range of the thermal gradient, where the chemistry is rich, but the temperatures have dropped enough to be survivable. The shrimp cluster on the chimney surfaces where the mineral extrusion provides grip and proximity to the source. The mussels arrange themselves in the lower zones, where the vent influence is gentler. The fish move through the space above. Even the microbial mats, invisible from this distance, but present on every solid surface throughout the field, have their zones, the aerobic communities at the outer surfaces and the anaerobic communities in the interior, each layer connected to the next by chemistry. The whole thing is ordered, not by intention, but by the simple logic of which organism can survive, which conditions, and within that logic, a kind of beauty persists. Structure emerges from constraint. The constraint is physical and chemical and does not care about the structure it produces. But the structure is there, a single hydrothermal vent field, viewed from above at a scale that takes in its full extent. A few hundred meters of active seafloor, the chimneys at the center, the rings of communities spreading outward, sits at the center of an enormous emptiness. In every direction beyond the field's edge, the abyssal plain extends, flat and cold and quiet, its sediment undisturbed except by the very occasional passing of a slow deep-sea creature moving across it. There is no vent chemistry here. There is almost nothing to eat. The organisms of the vent community, adapted to their particular chemical world, cannot cross this space. Their larvae drift in the current, and most are lost, descending through cold water without ever reaching another active field, settling into silence. Only a few reach the places where the chemistry rises again, where the heat finds a crack in the crust and forces its way upward, where the minerals precipitate and the chimneys begin to form. The larva that finds such a place settle and begin. Around the new vents, over years and then decades, the community assembles again. The same roles, the same layering, the same spatial logic of center and margin, of intense chemistry at the source and fading abundance toward the edge. The tube worms extend their plumes. The shrimp gather and press against the mineral walls. The crabs move their silky setae-covered claws through the warm water in the slow rhythm of cultivation. The mats spread across the rock. The fish arrive last, following the rest. Each community is an island. Between one island and the next, the distances are very great, not miles in the ordinary sense, but the distances of deep-sea biology, where even a few hundred miles of cold, featureless, food-poor water is effectively infinite for a vent-adapted larva. The communities diverge. They accumulate their own histories, their own species, their own arrangements of life around the same underlying chemistry. Separated by cold and dark and distance, each one becomes more itself over time, more particular, more specialized, more unlike anything that has assembled anywhere else along the ridge. What persists across all of them, what the tube worms and the shrimp and the yeti crabs and the pale fish all share, is the fundamental condition: warmth rising from below, chemistry from the planet's interior rather than light from the sun, life sustained entirely by the reaction of water and rock and heat. The food web rests on chemistry, on electrons, on the energy stored in molecular bonds, on the patient mineral reactions occurring inside rock that has never been touched by light. At the top of this web, the fish are ordinary hunters in many ways, reactive, quick to feed, as predatory as anything in the sunlit upper ocean. At the base, the chemistry is so old and so fundamental that the question of where geology ends and biology begins becomes difficult to answer cleanly. The mineral surface and the microbial mat are continuous. The rock and the organism are part of the same process, running at the same slow pace across the same slow time. The field of chimneys continues to vent into the dark water above it. The plumes rise. The organisms around the base of the structures move in their slow orbits, and the larger darkness beyond the community's edge holds nothing that is not already present: cold and pressure, and the faint sound of water moving through rock in the deep. The red plumes at the colony's center shift in the thermal current and catch the last of the light before the submersible turns away. The community does not watch it go. It continues as it was continuing before the light arrived, warm and chemical and alive in the long permanent dark. Inside the wall of a hydrothermal chimney, in a space no larger than a grain of sand, something is happening. The walls are mineral. The fluid moving through them is warm and alkaline and older in its chemistry than almost anything alive. No light reaches this place. No sound from the surface penetrates this depth, and yet the pore is not still. It breathes, in its way, warm fluid rising through from below, cold water pressing gently in from above, a slow and steady exchange across a boundary so thin it would be invisible to any instrument carried by human hands. This is the scale at which the question of life's beginning is now being seriously considered, not in the drama of a lightning bolt crossing a primordial sky, not in the violence of a meteor striking an ancient ocean. Here, in a space small enough to be lost inside the period at the end of a sentence, in the walls of a carbonate chimney sitting on a ridge of the Atlantic seafloor, in the continuous, patient, unhurried chemistry of rock meeting water, meeting warmth. The chimney itself rises 60 meters from the seafloor, taller than many trees, pale as old bone, its surface textured in the slow folds and ridges that mineral growth produces over centuries. It has been standing and venting for tens of thousands of years. It does not know this. It has no awareness of its own duration, but the rock records it anyway, in layers, in the crystalline architecture of its carbonate walls, in the way each new mineral coat wraps around the last like the rings of a tree that has never seen sunlight. The fluid rising through its interior is warm, not hot, not the violent superheated jets of other vent systems, but gently warm, around 40 or 60 degrees Celsius, moving upward with a kind of deliberate slowness that suits the scale of the place. It carries hydrogen. It carries methane. Its chemistry is profoundly alkaline, and the water pressing in from outside is not. Between the inside and the outside of a single chimney wall, across a thickness of mineral that a fingernail could scratch, there exists a difference in acidity that is not small. It is a difference that moves chemistry. It is a difference that, in the right conditions, drives a reaction. And it is this difference, this quiet, geological, fully non-biological voltage, that has drawn the attention of researchers working on the deepest problem in all of science. How does life begin? There are several good ideas and real evidence for more than one of them, and no way yet to be certain which is closest to the truth. What can be said, what the chemistry allows, is that the conditions inside an alkaline hydrothermal chimney are not random with respect to that question. They are, in ways that grow more specific, the more carefully they are examined, the right kind of conditions, not sufficient by themselves, not proven to have produced life, but the right kind, the kind worth looking at slowly, in the dark, with the patience the question deserves. The work of thinking carefully about this began in the early years of this century, when a small number of researchers, among them Nick Lane, William Martin, and Mike Russell, started to build a case that was not about lightning or meteors, but about rock and water and the slow passage of protons through a thin mineral wall. Their proposal was that the microscopic pores inside alkaline vent chimneys might have served as the first protocells, not living, not yet, but providing what a living cell would eventually need, a boundary between inside and outside, a surface for chemistry to occur on, and a source of energy that did not require the sun. A boundary, a surface, a source of energy. These are the three things a cell must have before it can be anything else at all. The pore inside the chimney wall provides all three in their simplest geological form. The mineral walls are the boundary. The iron-sulfur compounds embedded in those walls are the surface. And the proton gradient, the difference in acidity between the alkaline fluid inside and the more acidic water beyond, is the energy source. It is not a complicated arrangement. It is, in fact, about as simple as these things can be, which is precisely what makes it worth considering as a starting point. In every living cell on Earth today, the machinery that produces energy operates by moving protons across a membrane. This is not a minor detail. It is the central energy-generating mechanism of life, shared by bacteria, by archaea, by the cells of every plant and animal and fungus that has ever existed. The mechanism is called chemiosmosis, and it is universal in a way that almost nothing else in biology is, which raises a question that the chimney wall answers, at least in outline. Where did life learn to use proton gradients before it had membranes to move protons through? The vent chimney provides a proton gradient without any membrane at all. The alkaline fluid inside the pore and the relatively acidic ancient ocean pressing in from outside create a natural difference in hydrogen ion concentration across the mineral wall, a geological version of the same electrochemical difference that ATP synthase exploits in every living cell today. The machinery came later. The gradient was there first, written in the chemistry of the rock, Within the mineral walls of these chimneys, there are also iron-sulfur clusters. They are embedded in the carbonate matrix, small and crystalline, part of the rock itself. And iron-sulfur clusters are not unfamiliar to biology. At the catalytic cores of some of the most ancient enzymes, the ones that carry out the oldest forms of carbon fixation known, there are iron-sulfur clusters that bear a striking resemblance to those in the chimney walls. The resemblance is not cosmetic. It is structural, and it extends to their function. Both facilitate the movement of electrons in chemical reactions. Both sit at the center of processes that build carbon compounds from simpler molecules. The carbon fixation pathway considered most ancient is the Wood-Lungdahl pathway. It operates in methanogens and acetogens, some of the oldest lineages of microorganism known, and it is the simplest route from inorganic carbon dioxide and hydrogen to organic molecules. It uses iron-sulfur enzymes. It uses the kind of chemistry that requires no light, no oxygen, and no complex molecular machinery to get started. And it is the pathway operating today inside the microbial communities living in the warm pores of Lost City's carbonate chimneys, the same archaea that dominate those communities, metabolizing hydrogen and producing methane, running a form of carbon fixation that may be a direct biochemical echo of something that began in the mineral walls of a Hadean seafloor vent 4 billion years ago, before any cell existed to perform it. Before any cell. That phrase asks something of the imagination. 4 billion years is not a distance that can be walked to or a depth that can be dived to. It is a time so vast that every mountain range on Earth has risen and eroded and risen again within it. The continents have moved. The ocean chemistry has changed. The air has been remade. And yet the chemistry of hydrogen meeting carbon dioxide in the presence of iron-sulfur surfaces to produce organic molecules, that chemistry has not changed, because it does not need to. It is the chemistry of the universe, operating at the temperature and pressure and alkalinity that the serpentinizing seafloor provides, as patient and continuous as the rock itself. On the Hadean seafloor, 4 billion years ago, the conditions would have been different in scale, but not in kind, from what exists at Lost City today. Earth's crust at that time was largely ultramafic, rich in iron and magnesium, the minerals that serpentinize most readily. The ocean was more acidic, saturated with dissolved carbon dioxide from a thick and reducing early atmosphere. The geothermal heat was more intense, and serpentinization, the reaction between seawater and this mineral-rich crust, would have been widespread across the dark ocean floor, producing hydrogen, producing methane, building alkaline chimneys that stood in the acidic Hadean water and created across their mineral walls the same quiet proton gradients that Lost City creates today. No one was there to observe it. No instrument was present to record it. The rocks that held those first chimneys have been subducted and remelted and remade so many times that essentially nothing of them survives. The earliest chapters of this story are simply gone, written in a medium that could not last. What remains is the chemistry, the same chemistry running in the same way, in the same kinds of structures, at the same kinds of temperatures, in the carbonate towers of a field on the Atlantis Massif in the Atlantic Ocean at a depth of 700 or 800 feet below the surface. Lost City is not a fossil of the origin of life. It is a living analog, a system still operating, still producing the conditions, still running the chemistry that the earliest life may have used as a scaffold before it could build one of its own. The archaea in those chimneys are not ancestral life. They are modern organisms, highly evolved, shaped by billions of years of selection since whatever beginning there was. But the environment they inhabit and the basic chemical logic by which they sustain themselves may be the closest living approximation of the world in which the first metabolism began. The warm fluid continues to rise through the chimney pore, slow and mineral-rich, carrying dissolved hydrogen upward toward the cold ocean above. The mineral walls hold steady around it. The iron-sulfur surfaces sit embedded in the carbonate matrix, neither growing nor shrinking on any timescale a human life could register. And in the warm space of the pore, a chemistry runs that needs no sunlight, no surface, no air, only water, rock, and time. Time, and the patient pressure of protons moving through a wall. Far from the Atlantic, in the outer reaches of the solar system, a small moon orbits the ringed planet Saturn. It is called Enceladus, and from the outside it appears simple, white, smooth, cold, its surface mostly water ice, catching the faint and distant light of a sun that is nearly 1 billion miles away. It is small, roughly 300 miles across, a fraction of the size of Earth's moon. In the darkness of the Saturn system, it should be quiet, it should be inert. It should be exactly the kind of place that yields nothing of interest to the question of life, because it is cold and small and far, and life, as it was understood for most of scientific history, requires warmth and proximity to a star. But Enceladus is not quiet. From its southern polar region, a series of long fractures, called tiger stripes for their parallel arrangement, erupt almost continuously into space, sending geysers of water vapor and ice crystals hundreds of miles above the surface. The plumes are bright against the darkness. They are composed of water that has come from beneath the ice, from a global subsurface ocean that the ice shell conceals, an ocean that exists at temperatures far warmer than the surface because of tidal heating, the gravitational flexing of the moon's interior by Saturn's enormous pull, which generates heat deep in the rock. A spacecraft called Cassini, in orbit around Saturn for 13 years, flew through these plumes and tasted them. What it found was not just water, it found molecular hydrogen at concentrations suggesting active ongoing production. It found methane. It found carbon dioxide. It found silica nanoparticles of a kind that form only when hot water at high pressure interacts with silicate rock. And it found complex organic molecules, carbon-bearing compounds heavier and more complex than methane, the building blocks of further chemistry. Molecular hydrogen, methane, carbon dioxide, silica from hot rock-water interaction. This is the chemical signature of serpentinization. It is the same suite of compounds produced when seawater reacts with iron and magnesium-rich mantle rock, transforming olivine into serpentine, releasing heat and hydrogen in an exothermic reaction that fractures and expands the host rock and exposes new fresh surfaces to the circulating water. The same reaction that drives Lost City. The same reaction that may have sustained life's beginning on the Hadean seafloor. Somewhere beneath the ice of Enceladus, at the floor of its subsurface ocean, the chemistry suggests that rock is reacting with water in this way, slowly, continuously, in the dark, producing hydrogen, producing warmth, possibly building alkaline structures in the rock of the seafloor that stand against an acidic ocean and create across their mineral walls the quiet difference in chemistry that the hypothesis for the origin of life requires. Cassini did not descend to that seafloor. No instrument has. The ice shell of Enceladus is many miles thick, and the ocean beneath it has never been directly observed. What is known is the chemistry of the plumes and what the chemistry implies. The implication is not proof. it is not a confirmed detection of life, or of the structures that might produce it, or of anything more than the right ingredients in the right arrangement. But the right ingredients in the right arrangement is not a small thing when the question being asked is whether the chemistry that may have started life on Earth is happening anywhere else. The methane in the Enceladus plumes is particularly interesting, and the reason for its interest is something that takes a moment to arrive at fully. On Earth, methane in a geological context is often produced by serpentinization as a purely chemical byproduct of the water-rock reaction. But methane is also produced by living organisms, specifically by methanogens, the archaea that dominate Lost City's chimney communities, running the Wood-Lundahl pathway in warm alkaline pores and releasing methane as they fix carbon. Methane in the plumes of Enceladus could be geological, it could be biological, it could be both. There is, as of now, no way to know which it is, because distinguishing biological methane from geological methane requires measurements of isotopic ratios and molecular context that Cassini's instruments were not designed to perform with sufficient resolution. No one knows. This is a calm and settled position from which to consider the question, because it is the honest one. The plumes are there. The chemistry is there. The inference from the chemistry to a serpentinizing seafloor is well supported. Whether anything lives in the dark ocean beneath that seafloor is genuinely, openly, entirely unknown, and the not knowing is not a failure of science. It is the accurate frontier of what science has reached, and it is a very interesting frontier to be at. The faint light of Saturn falls on the surface of Enceladus without warming it. The surface temperature is around 300 degrees below 0 Fahrenheit. Nothing could live there, but the ice is irrelevant to the question, as irrelevant as the surface of the ocean is to what lives on the floor 2 miles below it. What matters is what is underneath, and underneath, in a dark ocean warmed by the tidal flexing of a moon in the gravity of a gas giant, the chemistry suggests warmth and water and rock and the patient ongoing reaction between them that has no need of sunlight to proceed. This thought deserves to rest for a moment before moving further. An ocean in a moon, orbiting Saturn, with a sea floor where serpentinization is likely occurring right now, at this moment, as these words settle into the dark. Hydrogen rising from rock, methane forming in the warm exchange between water and mineral, the same chemistry in the same configuration that may have produced the first metabolism on the floor of the Hadean Ocean 4 billion years ago, and that is certainly sustaining a complex and thriving ecosystem in the carbonate chimneys of Lost City today. The distance between Lost City and Enceladus, at its closest, is approximately 800 million miles. The chemistry is the same. Back inside the chimney pore, the warm fluid continues its slow rise. A single archaeal cell rests against the mineral wall, its membrane pressed against a surface threaded with iron-sulfur compounds, processing hydrogen, releasing methane, doing what it has done and what its ancestors have done in an unbroken line, stretching back through time far enough that the concept of duration begins to blur at the edges. The cell is not thinking about the Hadean Ocean. It is not aware of Enceladus. It is metabolizing, as it has always metabolized, in the warm alkaline dark of a mineral pore, drawing on a chemistry laid down by the geology of the planet long before anything alive was present to use it. The chimney around it has been standing for a very long time. The field of chimneys around it, pale, irregular, some short and collapsed, some still growing upward into the cold water above, has been present on the Atlantis Massif for tens of thousands of years, possibly longer. The massif itself, the The broad, flat-topped undersea mountain on which the field sits is a piece of the Earth's mantle exhumed and exposed by the slow rifting of the Atlantic. The serpentinization that drives Lost City is running in the peridotite of that mantle rock, the same iron and magnesium-rich material that dominated Earth's early crust, the same material that would have been widespread on the Hadean seafloor before continental growth changed the planet's surface character. Lost City is not a relic. It is not preserved from the ancient past. It is alive and actively venting, its chemistry running forward in real time, its microbial communities reproducing and metabolizing in the warm fluid of the present moment. But it carries within its geological logic a picture of an older world, a picture of what large portions of the early ocean floor might have looked like and what chemistry they might have sustained in the long ages before life became complex enough to leave a fossil record. The early ocean floor, dark and pressurized, covered in fractured peridotite, seawater seeping down through cracks in the rock, moving slowly into the warm depths, reacting with the olivine surfaces it encountered, and emerging transformed, warmer, more alkaline, carrying dissolved hydrogen and methane from chimneys standing on the seafloor in fields spread across the planet's oceanic crust. The proton gradient across the chimney walls, a silent geological voltage. The iron-sulfur surfaces inside those walls, facilitating the movement of electrons in reactions that build small organic molecules from carbon dioxide and hydrogen. And in those small molecules, perhaps, the beginning of the chemistry that would eventually, after a very long time, produce a membrane and a metabolism that could carry itself forward without the mineral wall, and something that could be called alive. No one knows exactly how that transition occurred. The step from a mineral pore with chemistry to a cell with a membrane is not a small one, and the intermediate stages, if they left any trace, left it in a medium that has long since been destroyed. There are good ideas. There is real evidence for the plausibility of each step in the sequence. The honest picture is one of a process running at a scale too small and too slow to have been observed in an environment too ancient and too thoroughly remade to yield direct evidence, producing a result, the first living cell, that changed the character of the planet without leaving a readable record of how it happened. This is not a cause for unease. The absence of a complete record is simply the nature of the question, and the question is large enough to remain worth asking in the absence of a complete answer. What is remarkable, and this word is used sparingly and meant precisely, is that the environment in which the answer is most likely to have been written still exists. Altered, certainly. The Hadean Ocean is gone, but the chemistry it hosted runs on in a field of pale chimneys on a slow ridge in the Atlantic, in the warm pores of mineral walls that have been building and dissolving and rebuilding for tens of thousands of years, attended by communities of archaea whose deepest metabolic logic may be a living record of the first reactions that sustained organic matter without sunlight, without oxygen, without any input from the biological world that had not yet begun. The warm fluid rises, the archaea metabolize. The hydrogen that serpentinization produces from the rock below diffuses upward through the mineral matrix and enters the chimney fluid and becomes available to any organism with the chemistry to use it. The process requires nothing from the surface world, not its light, not its oxygen, not the rain of organic particles that sustains the deep ocean floor, far from any vent. It is self-contained, it is self-sustaining. It has been running in various forms and at various sites across the ocean floor for as long as there has been an ocean and peridotite beneath it, and seawater to react with before any cell. That phrase again, with a slightly different weight now, because the chemistry that is running in the Lost City chimneys today does not require biology to maintain itself. The serpentinization proceeds without any organism participating in it. The proton gradient forms without any membrane to exploit it. The iron-sulfur surfaces catalyze their reactions without any enzyme to assist. The hydrogen accumulates and the carbon dioxide is present in the water, and the conditions for the simplest forms of carbon fixation are met continuously by a purely geological process that needs no help from anything alive. Life arrived at this chemistry. The chemistry did not arrive with life, and that order of events, the chemistry first, abundant and ongoing, creating conditions and gradients and surfaces that a proto-metabolism could find useful, is one of the reasons the alkaline vent hypothesis has the character it does. Not life struggling to emerge against an indifferent chemistry, but life as a continuation of a chemistry that was already running, already organized, already moving electrons and protons through a mineral system in ways that would eventually be recognizable as the core logic of a cell. The distinction is not merely semantic. It changes what life's beginning looks like. It changes the scale of what must be imagined. Not a single improbable event in a small warm pond, but a widespread and continuously renewed chemistry running across large portions of the early ocean floor, in millions of mineral pores, over millions of years, producing gradients and surfaces and reaction sequences that biological membranes and enzymes eventually learn to replicate in a portable form. Not a bolt of lightning, a long, slow, patient learning, if learning is the right word for a process that had no learner. It had no learner, no goal, no awareness of what was accumulating in those mineral pores. The rock reacted with the water because rock and water in those conditions always react that way. The hydrogen formed because it is a byproduct of the reaction and cannot be otherwise. The proton gradient existed because the fluid on one side of the wall and the fluid on the other had different chemistries, and that difference produced it, and it required nothing to sustain it except the ongoing geology of the planet. And in those pores, in that gradient, in those iron-sulfur surfaces, at some point, in conditions and by a sequence of steps that are still being worked out, something new began, something that could copy itself, something that could sustain a reaction, not by the accident of geological proximity, but by the evolved logic of a membrane and a metabolism, something small and improbable and fragile and tremendously consequential, because it did not stop, it persisted, it spread, it changed, and after a very long time, it filled every ocean and covered every continent, and eventually sent small machines to the bottom of the deep water to look at the chimneys it may have come from in the pale and ancient field at Lost City, where the hydrogen still rises from the rock and the archaea still metabolize in the warm mineral dark. The Enceladus plume rises above the southern pole of the small moon, white against the absolute black of the space between planets. From where Cassini observed it, Saturn's rings stretched in a broad pale band across the background, and the sun was a bright point rather than a disk, and the light that reached the moon's surface was perhaps 100th as strong as the light that falls on Earth at noon. The plume was brilliant against that background, a white arc of water vapor and ice catching the faint solar light as it erupted continuously from the fractures in the ice shell and dispersed into space. Inside the plume, too small and too distant for Cassini to observe directly, were the molecules that carried the chemical news from the ocean below. Molecular hydrogen, made somewhere in the dark beneath the ice by the reaction of water with rock. Methane? Possibly from the same reaction, possibly from something else. The question's still open. Carbon dioxide, present in the water as it is present in any ocean exposed to a carbon-bearing geology. And the silica, which was the most specific indicator, silica nanoparticles of a size and form that could only have formed in hot water under high pressure, dissolving silicate minerals from a warm rocky seafloor. A warm rocky seafloor far beneath the ice of a small moon orbiting Saturn, where the same chemistry that drives Lost City may be running right now in the dark, producing hydrogen, producing warmth, possibly building mineral structures, possibly creating the conditions that the chemistry of life requires before life begins. The possibility is not a certainty. It is an inference from chemistry to geology to conditions, and each step is well supported, and the step from conditions to life is genuinely unknown. There may be nothing alive in the ocean of Enceladus. The chemistry may be running in the dark without any organism present to use it, as the chemistry of Earth's early ocean floor may have run for a very long time before anything used it either. The duration between right conditions and the first metabolism is not known, and may not be the same in every ocean on every world. But the ocean is there, the chemistry is there, the serpentinization appears to be there, and the distance from Earth's ocean floor to Enceladus's ocean floor is, in one sense, very large, 800 million miles of cold vacuum, and in another sense, very small. It is the distance between two places where the same geology is producing the same chemistry, one of which we know sustained life, and one of which may or may not have done the same. The plume catches the faint light of the far sun and disperses slowly into space, its ice crystals spreading in a thin halo around the moon before they drift outward and are lost. The ocean beneath the ice continues. The rock below the ocean floor continues to react with the water that percolates through its fractures. The hydrogen continues to form, and the carbonate structures, if they exist in that dark ocean, continue to vent their warm alkaline fluid into the cold water above, creating across their mineral walls a gradient that requires no biology to form and no biology to sustain. Here, on the floor of the Atlantic, the Poseidon chimney stands in the dark, 60 meters tall, pale, its surface soft with the white carbonate texture that 60 or 70 degrees Celsius and tens of thousands of years of continuous growth produces. The warm fluid moves through it in slow upward plumes, carrying its dissolved hydrogen and methane into the cold water above, where the chemistry disperses and the microbial communities thin, and the mineral output of the chimney settles gradually toward the seafloor around it in a gentle, continuous drift of carbonate particles. The chimney will stand for a while longer. The geology that drives it shows no sign of exhaustion. Serpentinization is not a process that runs out quickly, because the reaction itself fractures the rock and exposes new fresh surfaces to the water, and the water is always present, and the peridotite of the Atlantis Massif extends for many kilometers below the seafloor, full of olivine that has not yet reacted, full of potential warmth and hydrogen waiting to be released by the contact with circulating seawater. In the pores of the chimney wall, the archaea metabolize. They have been metabolizing in chimneys like this one, in this field, or in others like it on other ridges on the ocean floor for a very long time. Not these individual cells which divide and are replaced as all cells are, but this metabolic strategy, this chemical approach to sustaining life, hydrogen from the rock, carbon dioxide from the water, organic molecules built from their combination, methane released as a byproduct. This approach is ancient in the lineage of life. The organisms that use it belong to some of the deepest branches of the tree of life, and the pathway they run may be the oldest form of carbon fixation that biology has produced. The deep branches of the tree of life lead back toward a common ancestor. All living things on Earth share one, a single population of cells from which every bacterium, every archaeon, every plant and animal, and fungus is descended, separated by billions of years of divergence, but united by the shared machinery of the ribosome, the shared logic of the genetic code, the shared use of ATP as a cellular energy currency, and the shared mechanism of chemiosmosis, protons moved across a membrane to drive a molecular machine. The last universal common ancestor used proton gradients. Before it, something must have provided proton gradients without a membrane to move them through. The mineral wall of an alkaline vent chimney provides proton gradients without a membrane. This was true on the Haitian seafloor. It is true at Lost City today. It may be true in the dark ocean of Enceladus.